For over 165 million years, massive dinosaurs walked the land, hunted, grazed, and shaped the world around them. Forests trembled beneath their weight. Oceans teemed with monsters. The sky wasn't empty, it had wings. It was a time of life on a scale we can hardly believe. Then, suddenly, it all ended. Not slowly, not quietly, but with an explosive disaster that changed the planet forever. Today we're still uncovering the truth, bone by bone, clue by clue. What was this ancient world really like, and what wiped it all away? This is the story of Earth's biggest mystery, and the rise and fall of its greatest creatures. Before we begin this journey, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below, and settle in for a fascinating prehistoric ride. Dinosaurs were a remarkable group of reptiles that dominated Earth's land for an astonishingly long period, spanning over 165 million years. Their reign began in the Triassic period, continued through the Jurassic, and concluded at the end of the Cretaceous period. This vast stretch of geological time, collectively known as the Mesozoic era, is often referred to as the Age of Dinosaurs. The term dinosaur itself, meaning terrible lizard, was coined in the 1840s by Sir Richard Owen, a British paleontologist, who recognised that these fossilised creatures possessed unique characteristics that set them apart from other reptiles. Despite the name, dinosaurs were not necessarily terrible in the sense of being evil, but rather awe-inspiring in their size and power. One of the most striking general characteristics of dinosaurs was their incredible diversity in size, shape, and lifestyle. They range from small chicken-sized animals like Compsognathus to colossal giants, such as the long-necked sauropods like Argentinosaurus, which could weigh as much as 80 tons and stretch over 100 feet long. Their body plans varied significantly. Some were bipedal, walking on two legs, like the fearsome Tyrannosaurus rex, while others were quadrupedal, moving on all four limbs, such as the armored Ankylosaurus or the horned Triceratops. Many dinosaurs possess scales similar to modern reptiles, and fossil evidence suggests some had feathers, particularly among the theropod group, which includes birds. The debate about whether dinosaurs were warm-blooded or cold-blooded has been ongoing, with current scientific consensus leaning towards a more active, higher metabolism than typical cold-blooded reptiles, perhaps even a form of warm-bloodedness. All known dinosaurs reproduced by laying eggs, similar to modern birds and reptiles, and fossilised nests and eggs provide valuable insights into their reproductive strategies and parental care. The enduring fascination with dinosaurs stems from several factors. Their immense size and raw power capture the imagination, evoking a sense of wonder about a lost world. The mystery surrounding their sudden disappearance at the end of the Cretaceous period, approximately 66 million years ago, adds another layer of intrigue. Furthermore, the scientific understanding that birds are direct descendants of dinosaurs provides a tangible link between these ancient giants and the world we inhabit today, making them less alien and more connected to contemporary life. Pop culture, through movies, books, and toys, has also played a significant role in cementing dinosaurs as iconic figures in the public consciousness, ensuring that each new generation discovers and marvels at these prehistoric creatures. The Mesozoic era is divided into three distinct periods, each witnessing different stages of dinosaur evolution and dominance. The Triassic period, from approximately 252 million to 201 million years ago, saw the first appearance of dinosaurs. These early forms were generally smaller and less dominant than other reptiles of the time. It was not until the Jurassic period, from about 201 million to 145 million years ago, that dinosaurs truly began to flourish and diversify. This period is often associated with the rise of the giant sauropods and large predatory theropods. Finally, the Cretaceous period, from 145 million to 66 million years ago, represented the peak of dinosaur diversity, with a wide array of specialized forms including horned dinosaurs, duck-billed dinosaurs, and the most famous large carnivores. Dinosaurs occupied a vast array of ecological niches, functioning as both herbivores and carnivores. Herbivorous dinosaurs like Diplodocus and Stegosaurus developed various adaptations for processing plant material, from long necks to reach high foliage to specialized teeth for grinding tough vegetation. Carnivorous dinosaurs such as Velociraptor and Giganotosaurus were apex predators, equipped with sharp teeth and claws for hunting and tearing flesh. The classification of dinosaurs broadly falls into two main groups based on the structure of their hip bones: the Ornithischia, or bird-hipped dinosaurs, which included most herbivores like Triceratops and Stegosaurus, and the Saurischia, or lizard-hipped dinosaurs, which encompassed both the long-necked sauropods and the carnivorous theropods. This hip structure distinction, however, is not directly related to the bird dinosaur lineage, as birds evolved from a group of lizard-hipped dinosaurs. For 165 million years, dinosaurs were the undisputed kings of the land. Their long reign is a testament to their evolutionary success and adaptability across various environments. While dinosaurs dominated terrestrial ecosystems, other large reptiles also thrived during the Mesozoic era, but occupied different ecological roles. Pterosaurs, often mistakenly called flying dinosaurs, were a distinct group of flying reptiles with leathery wings soaring through the skies. Marine reptiles such as ichthyosaurs, plesiosaurs and mosasaurs were formidable predators of the ancient seas, evolving streamlined bodies and powerful flippers for aquatic life. These groups, while coexisting with dinosaurs, were not dinosaurs themselves, highlighting the specific definition of Dinosauria as primarily terrestrial animals with a particular hip and limb structure. The scientific study of dinosaurs, known as paleontology, began in earnest in the early 19th century with the discovery of the first recognised dinosaur fossils in England. Gideon Mantell, a physician, discovered the teeth of Iguanodon in the 1820s, followed by William Buckland's description of Megalosaurus. These initial finds sparked immense public and scientific interest, leading to a global dinosaur rush in the late 1800s, particularly in North America, where vast bone beds yielded incredible discoveries. The process of fossilization, which allows us to study these ancient creatures, typically involves the rapid burial of an organism's remains in sediment, protecting them from scavengers and decay. Over millions of years, minerals in the surrounding water replace the organic material of bones, turning them into rock. These fossilized remains provide invaluable clues about dinosaur anatomy, behavior, and the environments they inhabited. Ongoing scientific research continues to unravel the mysteries of dinosaurs. New fossil discoveries are made regularly, often leading to the description of previously unknown species or providing fresh insights into existing ones. Advanced technologies such as CT scanning and three-dimensional modelling allow paleontologists to study fossils in unprecedented detail, revealing internal structures, muscle attachments, and even brain cavities. Biomechanical studies help scientists understand how dinosaurs moved, ran, and hunted. Chemical analyses of fossilized bones and teeth can reveal aspects of their diet, growth rates, and even their physiology. The study of fossilized footprints, known as trackways, offers direct evidence of dinosaur locomotion, herd behavior, and interactions. The field of paleontology is dynamic, constantly evolving as new evidence emerges, deepening our understanding of these magnificent creatures that once roamed our planet. The legacy of the dinosaur era continues to inspire scientific inquiry and public imagination, reminding us of the incredible history of life on Earth. To understand the world into which dinosaurs emerged, it is essential to look back at the geological period immediately preceding their appearance, the Permian period. This period, which spanned from approximately 299 million to 252 million years ago, was a time of significant geological and biological change, culminating in the most severe mass extinction event in Earth's history. The dominant geological feature of the Permian was the formation of the supercontinent Pangaea. Throughout the Permian, Earth's major landmasses gradually converged, driven by plate tectonics, to form a single, enormous continent that stretched from pole to pole. This colossal landmass profoundly influenced global climate patterns and the distribution of life. The formation of Pangaea led to a climate characterized by extreme seasonality and vast interior deserts. With most of the land concentrated in one large mass, oceanic influences were limited to the coastal regions. The interior of Pangaea experienced hot, arid conditions, leading to widespread desertification. Coastal areas, however, were subject to strong monsoonal weather systems, bringing seasonal rains. This stark contrast in environments created diverse habitats, but also presented significant challenges for life, particularly in the vast, dry continental interior. The assembly of Pangaea also led to the formation of extensive mountain ranges, further influencing regional climates and creating rain shadows. The life forms that dominated the late Permian were distinct from the reptiles that would later become dinosaurs. The terrestrial ecosystems were largely ruled by synapsids, often referred to as mammal-like reptiles. These animals, which were the ancestors of mammals, exhibited a range of forms and sizes. Early Permian synapsids included creatures like Dimetrodon, famous for its large sail on its back, which likely served a thermoregulatory purpose. Later Permian synapsids, such as the Gorgonopsians, were formidable predators with saber-like teeth, while Dicynodonts were common herbivores. These synapsids were highly diverse and occupied many of the ecological niches that would later be filled by dinosaurs. Alongside synapsids, early reptiles, amphibians, and insects also thrived in various environments, contributing to a rich and complex Permian ecosystem. The Permian period came to a cataclysmic end with the Permian-Triassic extinction event, often dubbed the Great Dying. This event, occurring approximately 252 million years ago, was by far the most devastating mass extinction in Earth's history. It wiped out an estimated 90% of all marine species and 70% of all terrestrial vertebrate species. The primary cause of this extinction is widely believed to be massive and prolonged volcanic eruptions in what is now Siberia, forming the Siberian Traps. These eruptions released enormous quantities of greenhouse gases, such as carbon dioxide and methane, into the atmosphere, leading to rapid and extreme global warming. This warming, in turn, caused widespread ocean anoxia, meaning a severe depletion of oxygen in the oceans, which suffocated marine life. The high temperatures also led to the release of toxic hydrogen sulfide from the oceans, further poisoning the atmosphere and land. The sheer scale and speed of these environmental changes overwhelmed most life forms, leading to a dramatic collapse of ecosystems worldwide. The early Triassic period, following the Great Dying, was a time of recovery and ecological restructuring. For millions of years after the extinction, Earth's ecosystem were relatively sparse and simplified. The biodiversity that had characterized the Permian was severely depleted, and the surviving species faced a world transformed by environmental upheaval. This period of recovery, sometimes referred to as the recovery interval, saw the gradual re-establishment of food webs and the slow diversification of surviving lineages. The dominant terrestrial animals of the early Triassic were often small, hardy generalists, capable of surviving in the harsh post-extinction environment. The climate of Pangaea in the early Triassic remained largely hot and arid, with the vast continental interior still experiencing desert conditions. Monsoonal patterns continued to influence coastal regions. This global climate, while challenging, also provided opportunities for certain groups of organisms that could adapt to these conditions. The plant life of the early Triassic was dominated by hardy, drought-resistant species such as conifers, ferns, and cycads. These plants formed the base of the terrestrial food chain, supporting the surviving herbivorous animals. Flowering plants, which would become dominant much later, had not yet evolved. Among the survivors of the Permian-Triassic extinction were certain groups of reptiles. These reptiles, particularly the archosauromorphs, were poised to diversify and eventually give rise to the dinosaurs. Archosauromorphs were a broad group that included the ancestors of crocodiles, pterosaurs, and dinosaurs. They possessed several key adaptations that allowed them to thrive in the Triassic environment, such as more upright postures compared to earlier sprawling reptiles, which allowed for more efficient locomotion. Their respiratory systems were also likely more efficient, enabling them to cope with lower oxygen levels or higher temperatures. The early archosaurs were a diverse group that competed for resources and ecological space. Many of these early archosaurs were not dinosaurs, but were their close relatives or evolutionary cousins. For example, phytosaurs were large, crocodile-like predators that lived in aquatic environments, resembling modern crocodiles but with nostrils located near their eyes. Etosaurs were heavily armoured, herbivorous reptiles that looked somewhat like armoured tanks. Rauisuchians were large, agile predators that walked with a semi-erect posture, making them formidable hunters in the Triassic landscape. These non-dinosaurian archosaurs were often larger and more dominant than the very first dinosaurs during the early and mid-Triassic, illustrating that the rise of dinosaurs was not an immediate takeover, but a gradual process within a competitive environment. The legacy of the Permian extinction and the subsequent early Triassic recovery period created a unique evolutionary landscape, setting the stage for the eventual emergence and diversification of the magnificent creatures that would define the Mesozoic era. The Triassic period, spanning from approximately 252 million to 201 million years ago, marks a pivotal chapter in Earth's history, as it was during this time that the very first dinosaurs emerged. This period followed the most devastating mass extinction event in Earth's history, the Great Dying, which had profoundly reshaped global ecosystems. The Triassic was a time of recovery, diversification, and intense competition among various reptile groups, ultimately setting the stage for the Mesozoic era's iconic giants. The climate of the Triassic period was largely influenced by the presence of the supercontinent Pangaea. With most of Earth's landmass consolidated into a single vast continent, global climate patterns were distinct from today. The interior of Pangaea experienced extreme aridity, leading to widespread deserts and strong temperature fluctuations between day and night. Coastal regions, however, were subject to powerful monsoonal weather systems, bringing seasonal heavy rainfall. Overall, the Triassic climate was generally warmer than the present day, with little evidence of polar ice caps. This warm, largely arid environment, punctuated by seasonal rains, shaped the flora and fauna that evolved during this time. The plant life was dominated by conifers, cycads, and ferns, forming the primary food source for herbivorous animals. Flowering plants had not yet appeared. Before dinosaurs rose to prominence, the terrestrial ecosystems of the early and mid-Triassic were dominated by a diverse array of archosaurs and other reptiles. Archosaurs were a group of reptiles that included the ancestors of crocodiles, pterosaurs, and dinosaurs. Many of these early archosaurs were formidable creatures that occupied the top predator niches and filled various ecological roles. For instance, phytosaurs were large, semi-aquatic predators that bore a striking resemblance to modern crocodiles, though their nostrils were positioned near their eyes rather than at the tip of their snouts. Etosaurs were heavily armoured, plant-eating reptiles that looked like walking tanks, with bony plates covering their bodies. Rauisuchians were a group of large, agile quadrupedal predators that walked with an upright or semi-erect posture, making them highly efficient hunters. These non-dinosaurian archosaurs were often larger and more widespread than the earliest dinosaurs, illustrating that the initial appearance of dinosaurs did not immediately lead to their global dominance. Instead, they were part of a diverse reptilian fauna, competing for resources and survival. The evolutionary context for the emergence of dinosaurs was one of gradual diversification rather than a sudden explosion. Dinosaurs did not simply appear and immediately take over. Their rise was a slow process, occurring within a competitive landscape. The first definitive dinosaurs appeared in the fossil record during the Middle to Late Triassic, approximately 230 million years ago. These earliest known dinosaurs were relatively small compared to their later descendants, and to many of the other archosaurs living at the time. Among the earliest and most well-known dinosaurs are Earaptor, Herrerasaurus, and Staurikosaurus. Earaptor, discovered in Argentina, is one of the most primitive dinosaurs known. It was a small bipedal animal, about 3 feet long, and likely an omnivore or a very early carnivore. Herrerasaurus, also found in Argentina, was larger, reaching lengths of up to 20 feet, and was a clear predator possessing sharp teeth and claws. Staurikosaurus, another South American find, was similar in size to Earaptor and also a bipedal carnivore. These early dinosaurs shared several key anatomical features that distinguished them from other archosaurs, such as a more upright posture with limbs held directly beneath the body, allowing for more efficient locomotion and potentially higher activity levels. Initially, these early dinosaurs occupied relatively modest ecological niches. They were not the apex predators of their time. That role was often filled by the larger Rauisuchians. The first dinosaurs were likely opportunistic hunters of smaller animals or scavengers, coexisting with and often being overshadowed by the more dominant non-dinosaurian archosaurs. Their small size and agile build may have allowed them to exploit resources that were less accessible to their larger competitors, giving them a survival advantage in certain circumstances. Throughout the Triassic period, dinosaurs slowly began to diversify. While the earliest forms were primarily small, bipedal carnivores, by the late Triassic, other body plans and dietary preferences started to emerge. One significant development was the appearance of early sauropodomorphs, the ancestors of the long-necked sauropods that would dominate the Jurassic. Plateosaurus, a well-known late Triassic sauropodomorph from Europe, was a large bipedal or facultatively quadrupedal herbivore, reaching lengths of up to 30 feet. Its existence indicates that plant-eating dinosaurs were becoming increasingly important components of Triassic ecosystems. Other groups, such as early ornithischians, the bird-hipped dinosaurs, also made their first appearances, though they remained relatively rare compared to the saurischians, the lizard-hipped dinosaurs, during the Triassic. The end of the Triassic period was marked by another significant mass extinction event, the Triassic-Jurassic Extinction, which occurred approximately 201 million years ago. While not as devastating as the Great Dying, this event had a profound impact on life, particularly on land. It led to the disappearance of many of the large non-dinosaurian archosaurs, including most of the Rauisuchians and phytosaurs, as well as many large amphibians and marine reptiles. The exact causes of this extinction are still debated, but evidence points towards massive volcanic activity associated with the breakup of Pangaea, specifically the Central Atlantic Magmatic Province. These eruptions would have released vast amounts of greenhouse gases, leading to rapid global warming and ocean acidification, similar to the Permian extinction but on a smaller scale. Crucially, the Triassic-Jurassic extinction event cleared the ecological playing field for dinosaurs. While many other large land animals perished, dinosaurs, which had already diversified to some extent, survived and were able to fill the newly vacated niches. This event was not a direct cause of dinosaur evolution, but it was the catalyst that allowed them to become the dominant terrestrial vertebrates of the subsequent Jurassic and Cretaceous periods. Without the removal of their major competitors, the age of dinosaurs might have looked very different, or perhaps never happened at all. Thus the Triassic, with its unique climate, diverse early archosaurs, and the critical end Triassic extinction, was indeed the essential beginning of the dinosaur era. The Jurassic period, spanning from approximately 201 million to 145 million years ago, represents the middle chapter of the Mesozoic era, and is often celebrated as the golden age of the giant dinosaurs. Following the Triassic-Jurassic extinction event, which cleared many of the ecological niches previously occupied by other large archosaurs, dinosaurs were poised to become the dominant terrestrial vertebrates. This period witnessed an unprecedented increase in the size of many dinosaur lineages, particularly among the long-necked herbivores, leading to some of the largest land animals that have ever existed. Geologically, the Jurassic period was characterized by the continued breakup of the supercontinent Pangaea. The initial rifting that began in the Triassic accelerated, leading to the separation of Laurasia, North America and Eurasia, from Gondwana, South America, Africa, Antarctica, Australia and India. As these land masses drifted apart, new oceans began to form, and rising sea levels created vast shallow seas and inland waterways. This continental drift had a profound impact on global climate. While the Triassic was largely arid, the Jurassic saw a generally warmer and more humid climate with increased rainfall. This shift in climate fostered lush vegetation across much of the globe, providing an abundant food supply for the burgeoning populations of herbivorous dinosaurs. The dominant plant groups remained conifers, cycads, ginkgos, and ferns, forming vast forests and open woodlands. The most iconic and truly gigantic dinosaurs of the Jurassic were the sauropods. These long-necked, long-tailed quadrupedal herbivores evolved to truly immense proportions during this period. Their sheer size offered several advantages, including defense against large predators and the ability to reach high foliage that was inaccessible to smaller animals. Sauropods possessed several anatomical adaptations that facilitated their gigantism. Their bones were often hollow or filled with air sacs, similar to birds, which reduced their overall weight while maintaining structural integrity. Their columnar limbs were built like elephant legs, designed to support enormous weight. Their long necks, supported by numerous vertebrae, allowed them to browse on vegetation over a wide area without moving their bodies, conserving energy. One of the most famous Jurassic sauropods was Brachiosaurus, meaning arm lizard, known for its exceptionally long front legs, which made its shoulders higher than its hips, giving it a giraffe-like posture. Brachiosaurus could reach lengths of around 85 feet and weighed an estimated 50 tons, allowing it to browse on the highest leaves of tall conifer trees. Its nostrils were positioned on top of its head, a feature once thought to suggest a semi-aquatic lifestyle, but now understood to be related to its respiratory system. Another well-known sauropod was Diplodocus, meaning double beam, named for the unique chevron bones on the underside of its tail vertebrae. Diplodocus was incredibly long, reaching lengths of up to 90 feet but was relatively slender, weighing around 15 tons. It likely used its long neck to sweep through low-lying vegetation or to reach moderate heights, and its whip-like tail may have been used for defense or communication. Apatosaurus, formerly known as Brontosaurus, was another massive Jurassic sauropod, reaching lengths of up to 75 feet and weighing around 25 tons. It had a robust build and a powerful tail. Camarasaurus, meaning chambered lizard, was a more common and somewhat smaller sauropod, typically around 50 feet long and weighing 20 tons. It had a relatively short, deep skull and spoon-shaped teeth, indicating it was a browser that likely fed on tougher vegetation. The sheer number and variety of sauropods across different continents during the Jurassic period underscore their ecological success and the abundance of plant resources available to support such large populations. These giants likely lived in herds, providing safety in numbers and facilitating migration to new feeding grounds. While sauropods dominated the large herbivore niches, the Jurassic also saw the evolution of other remarkable dinosaur groups, including the armoured stegosaurs. These medium to large herbivores were characterized by rows of distinctive plates along their backs and formidable spikes on their tails. The most famous example is Stegosaurus, meaning roof lizard, which lived in North America during the late Jurassic. Stegosaurus was about 26 feet long and weighed around 5 tons. Its most striking features were the 17 bony plates, called scutes, embedded in its skin along its back. The exact function of these plates has been a subject of much debate among paleontologists. Theories include defense against predators, thermoregulation, using the plates to absorb or release heat, or display for mating or species recognition. Equally distinctive were the 4 sharp spikes on Stegosaurus's tail, collectively known as a thagomizer, a term popularized by a cartoon and now widely adopted in scientific circles. These spikes, which could be up to 3 feet long, were undoubtedly a powerful defensive weapon against predators. Despite its large body, Stegosaurus had a remarkably small head and a tiny brain, about the size of a walnut, leading to early misconceptions about dinosaur intelligence. It was a low-level browser, feeding on ferns, cycads, and other low-growing plants. Its relatively short front limbs and longer hind limbs suggest it might have reared up on its hind legs to reach slightly higher vegetation. The presence of such massive herbivores naturally led to the evolution of large carnivorous predators to keep their populations in check. The dominant large theropods of the Jurassic were formidable hunters. Allosaurus, meaning different lizard, was one of the most common and widespread large predators of the late Jurassic in North America. It could reach lengths of up to 39 feet and weighed around 2 tons. Allosaurus possessed powerful jaws filled with serrated teeth, robust limbs, and sharp claws, making it an efficient predator of medium to large herbivores, including juvenile sauropods and stegosaurs. Fossil evidence, including bite marks on bones and trackways, suggests that Allosaurus may have hunted in packs, allowing them to take down even larger prey. Another notable Jurassic theropod was Ceratosaurus, meaning horn lizard, named for the distinctive horn on its snout. It was a medium-sized predator, typically around 20 feet long, and coexisted with Allosaurus. Its powerful jaws and relatively short, deep skull indicate a strong bite force. While terrestrial dinosaurs were the main focus of the Jurassic, the period also saw the continued diversification of marine reptiles and pterosaurs. While terrestrial dinosaurs were the main focus of the Jurassic, the period also saw the continued diversification of marine reptiles and pterosaurs. Ichthyosaurs, resembling modern dolphins, were highly adapted to aquatic life, while long-necked plesiosaurs and short-necked plesiosaurs were formidable marine predators. Pterosaurs, the flying reptiles, continued to evolve, with species like Pterodactylus soaring through the skies. These groups, while not dinosaurs themselves, were integral parts of the broader Jurassic ecosystems. The Jurassic period thus stands as a testament to the incredible evolutionary potential of dinosaurs, showcasing their ability to reach unprecedented sizes and diversify into a variety of forms that dominated the land for tens of millions of years. The Cretaceous period, spanning from approximately 145 million to 66 million years ago, represents the final and most diverse chapter of the dinosaur age. This period was a time of significant geological, climatic, and biological change, which profoundly influenced the evolution and diversification of dinosaur lineages. The ongoing breakup of Pangaea continued, leading to the formation of continents that began to resemble their modern configurations. South America separated from Africa, India drifted northwards, and North America and Eurasia continued to split. This continental rearrangement led to increased volcanic activity, rising sea levels, and the creation of numerous shallow inland seas, such as the Western Interior Seaway that divided North America. These geographical changes resulted in more varied climates across the globe, with distinct latitudinal zones, though the overall global temperatures remained warmer than today. Perhaps the most significant biological event of the Cretaceous period, apart from the dinosaurs themselves, was the widespread evolution and diversification of flowering plants, or angiosperms. While conifers, cycads, and ferns had dominated the Jurassic landscape, angiosperms rapidly diversified during the Cretaceous, becoming a major component of terrestrial ecosystems. Their evolution introduced new food sources such as fruits and flowers, and created new types of habitats. This floral revolution had a direct impact on the evolution of herbivorous dinosaurs, leading to the rise of highly specialized plant eaters. Among the most successful and diverse groups of herbivorous dinosaurs in the Cretaceous were the hadrosaurs, often referred to as duck-billed dinosaurs due to their broad, flattened snouts. Hadrosaurs were incredibly numerous and widespread, becoming the dominant large herbivores in many late Cretaceous ecosystems, particularly in North America and Asia. They were typically large, bipedal or facultatively quadrupedal animals, reaching lengths of up to 50 feet. Their most remarkable feature was their complex dental battery, consisting of hundreds of tightly packed teeth arranged in multiple rows. These teeth were continuously replaced and formed a grinding surface, allowing hadrosaurs to efficiently process tough fibrous plant material, including conifers and the newly evolving flowering plants. Hadrosaurs exhibited a wide range of crests and other cranial ornaments, which varied significantly between species. These crests, made of bone, were often hollow and connected to the nasal passages. While their exact function is debated, it is widely believed that they were used for visual display, species recognition, or perhaps for producing vocalizations to communicate within herds. For example, Parasaurolophus possessed a long, backward-projecting tubular crest that may have functioned as a resonating chamber for deep calls. Edmontosaurus, on the other hand, had a relatively flat skull, though some individuals preserved a fleshy comb-like crest. Fossil evidence, including vast bone beds, indicates that hadrosaurs lived in large herds, suggesting complex social behaviors. Discoveries of fossilized nests and eggs also suggest that some hadrosaurs engaged in parental care, with juveniles remaining in nesting colonies for a period after hatching. Another highly successful and iconic group of Cretaceous herbivores were the ceratopsians, or horned dinosaurs. These quadrupedal dinosaurs were characterized by their prominent facial horns and elaborate bony frills extending over their necks. Ceratopsians were particularly abundant in late Cretaceous North America and Asia. Their frills, often adorned with spikes or bumps, varied greatly in size and shape among different species. While they provided protection for the neck, they also likely served as display structures for attracting mates or intimidating rivals, and possibly for thermoregulation. The horns, which could be one or more, were formidable weapons used for defense against predators and for intraspecific combat, as evidenced by healed wounds on fossilized skulls. The most famous ceratopsian is Triceratops, meaning three-horned face, a massive animal that could reach lengths of 30 feet and weigh up to 10 tons. It possessed two large brow horns and a shorter nasal horn, along with a large solid frill. Styracosaurus, another well-known ceratopsian, had a single large nasal horn and 6 long spikes projecting from the edge of its frill. Ceratopsians were low-level browsers, using their powerful beaks to snip off tough vegetation. Their powerful jaws and shearing teeth allowed them to process fibrous plants. The diversity within ceratopsians, from the giant Triceratops to smaller, more primitive forms, showcases their evolutionary success. The diversification of herbivorous dinosaurs naturally led to the evolution of new and increasingly specialized carnivorous predators. The late Cretaceous saw the emergence of some of the most famous and fearsome theropods. Tyrannosaurus rex, meaning tyrant lizard king from North America, is arguably the most iconic dinosaur of all time. Reaching lengths of up to 40 feet and weighing over 7 tons, Tyrannosaurus rex possessed massive jaws and banana-sized serrated teeth capable of crushing bone. While its small two-fingered forelimbs remain a subject of curiosity, its powerful hind limbs and massive head indicate it was a formidable predator, likely both an active hunter and a scavenger. In other parts of the world, different apex predators reigned. Giganotosaurus from South America was even larger than Tyrannosaurus rex, reaching lengths of over 40 feet, though it was more lightly built. Spinosaurus from North Africa was a unique and massive theropod, distinguished by its enormous sail-like structure on its back and crocodile-like snout. Recent discoveries suggest Spinosaurus was highly adapted for a semi-aquatic lifestyle, preying on large fish and other aquatic animals. Other diverse theropod groups included the heavily armoured club-tailed ankylosaurs, the dome-headed pachycephalosaurs, the ostrich-like ornithomimids, and the agile, sickle-clawed dromaeosaurids, often referred to as raptors, such as Velociraptor from Mongolia. The Cretaceous period also saw the continued evolution of flying reptiles, the pterosaurs, which reached their largest sizes with giants like Quetzalcoatlus, possessing a wingspan of up to 36 feet. Marine reptiles, including the long-necked plesiosaurs and the powerful serpentine mosasaurs, continue to dominate the oceans. Crucially, the Cretaceous was also the period when true birds, evolving from small feathered theropods, diversified significantly, coexisting with their non-avian dinosaur relatives. The rich fossil record of the Cretaceous reveals a complex and interconnected web of life, with highly specialized dinosaurs occupying nearly every terrestrial niche. This peak of dinosaur diversity, however, would ultimately be brought to an abrupt end by the KPG extinction event at the close of the period, concluding their 165 million year reign. Dinosaurs, over their 165 million year reign, inhabited a vast array of environments across the globe, adapting to diverse climates and landscapes. Their distribution was not confined to a single type of terrain. Rather, they thrived in everything from lush, humid forests to open, semi-arid plains, swampy wetlands, and even polar regions. The geological evolution of Earth, particularly the breakup of the supercontinent Pangaea, played a crucial role in shaping these varied habitats and influencing the types of dinosaurs that lived in them. During the Triassic period, when dinosaurs first emerged, Pangaea was largely intact, resulting in a global climate characterized by extreme seasonality and vast interior deserts. Early dinosaurs, like Eoraptor and Ararosaurus, lived in regions that were likely semi-arid or had strong monsoonal patterns, with seasonal rainfall supporting sparse vegetation. As Pangaea began to rift apart in the Jurassic and Cretaceous periods, new oceans formed and continental landmasses drifted into different latitudinal zones. This led to a more varied global climate, with increased humidity and the development of distinct climate zones. though overall temperatures remained significantly warmer than today, with no permanent polar ice caps for much of the Mesozoic. Dense forests were a prominent habitat throughout the Mesozoic era. These forests were not composed of the broadleaf trees common today, but rather dominated by conifers, such as relatives of modern pines, spruces and sequoias, as well as cycads and ginkgos. These towering trees provided abundant food for large browsing dinosaurs and offered shelter and hunting grounds for predators. Large sauropods, like Brachiosaurus and Camarasaurus, would have browsed on the high canopy leaves, while medium-sized herbivores, such as stegosaurs, fed on lower-growing vegetation. Smaller, agile theropods might have used the dense undergrowth for ambush hunting. The presence of fossilized tree trunks and leaf impressions in sedimentary rocks provides direct evidence of these ancient forest ecosystems. Vast plains and open woodlands also characterize large portions of the Mesozoic continents. These expansive areas, often with scattered trees and abundant low-lying vegetation like ferns and horsetails, would have supported large herds of grazing and browsing dinosaurs. Hadrosaurs, with their specialized dental batteries for processing tough plant material, were particularly well suited to these environments during the Cretaceous. Similarly, the immense sauropod herds of the Jurassic likely roamed these plains, moving between feeding grounds. The open nature of these habitats would have favored large, fast-moving predators like Allosaurus and Tyrannosaurus rex, which could pursue their prey across open terrain. Fossilized trackways showing multiple dinosaur footprints moving in the same direction offer compelling evidence of herd behavior in these open landscapes. Swampy wetlands and extensive river deltas were another crucial habitat for many dinosaurs. These areas, characterized by abundant water, lush vegetation, and soft, muddy ground, would have been rich in resources. Plants like horsetails, ferns, and early angiosperms would have thrived in these moist conditions. Some sauropods, like Diplodocus, with their long, relatively lightweight bodies, might have navigated these areas, feeding on aquatic or semi-aquatic plants. The unique Spinosaurus, with its crocodile-like snout and adaptations for a semi-aquatic lifestyle, is a prime example of a predator specifically adapted to riverine and swamp environments, preying on large fish and other aquatic creatures. The soft sediments of these wetlands were also ideal for preserving footprints and other trace fossils, providing detailed insights into dinosaur behavior and locomotion. Coastal areas, bordering the shallow inland seas and newly forming oceans, also supported diverse dinosaur populations. While dinosaurs were primarily terrestrial, some species may have lived near the coast, feeding on coastal vegetation or scavenging along the shorelines. The presence of large marine reptiles such as plesiosaurs and mosasaurs, and flying reptiles, the pterosaurs, meant that coastal dinosaurs would have coexisted with these other Mesozoic giants. Fossil discoveries in coastal sedimentary formations indicate that various dinosaur types, including some theropods and ornithopods, inhabited these transitional zones between land and sea. Remarkably, fossil evidence indicates that dinosaurs also inhabited polar regions, which, while warmer than today, would still have experienced periods of prolonged darkness during winter. Discoveries in places like Alaska and Antarctica have revealed species adapted to these conditions. For instance, the small ornithopod Liaelinosaura from Australia, which was part of Antarctica during the Cretaceous, had unusually large eye sockets, suggesting adaptations for low-light conditions. These polar dinosaurs might have migrated seasonally or possessed physiological adaptations to cope with the colder temperatures and extended periods of darkness. The presence of dinosaurs in these diverse environments underscores their incredible adaptability and resilience as a group. Beyond these broad categories, specific geological features also shaped dinosaur habitats. Areas with active volcanism, particularly during the Triassic and Cretaceous, would have created unique, albeit challenging, landscapes. Rivers and lakes provided essential water sources and carved out valleys and floodplains, creating fertile areas for plant growth and migration corridors for animals. Mountain ranges, formed by tectonic activity, would have created rain shadows, leading to arid regions on one side and wetter conditions on the other, further diversifying the available habitats. The distribution of specific dinosaur species was often closely tied to the particular environmental conditions and food sources available in their preferred habitats. The fossil record provides a rich tapestry of evidence, allowing paleontologists to reconstruct these ancient worlds and understand the intricate relationships between dinosaurs and their diverse homes. The dietary habits of dinosaurs were as diverse as the creatures themselves, spanning a vast spectrum from dedicated plant eaters to formidable flesh eaters, and even some that likely consumed a mix of both. Understanding what dinosaurs ate is crucial for reconstructing ancient ecosystems, as it reveals the intricate food webs that sustained these magnificent animals for over 165 million years. Paleontologists infer dinosaur diets primarily from fossil evidence, including the shape and arrangement of teeth, jaw structure, digestive systems, and rare finds like fossilized stomach contents or coprolites, which are fossilized dung. The vast majority of dinosaur species were herbivores, meaning they subsisted entirely on plant material. These plant-eating dinosaurs evolved a remarkable array of adaptations to process the tough, fibrous vegetation of the Mesozoic era. The most iconic herbivorous dinosaurs were the sauropods, the immense long-necked and long-tailed giants of the Jurassic and Cretaceous periods. Sauropods, such as Brachiosaurus, Diplodocus, and Apatosaurus, consumed truly prodigious amounts of plant matter to fuel their enormous bodies. Their long necks allowed them to browse on high foliage in tall conifer trees, or sweep across wide areas of lower-lying vegetation, effectively acting as living lawnmowers or pruning shears. Their teeth were generally peg-like or spoon-shaped, suited for stripping leaves or branches rather than extensive chewing. After swallowing, the food would travel to a large stomach or gizzard where it would be broken down. Many sauropod fossils are found with gastroliths, or stomach stones, which these dinosaurs swallowed to help grind up tough plant material in their digestive tracts, similar to how modern birds use grit. The sheer volume of food required by these massive animals suggests a near-constant state of feeding throughout their lives. Among the bird-hipped dinosaurs or ornithischians, herbivory reached a high degree of specialization. The hadrosaurs or duck-billed dinosaurs of the Cretaceous period, such as Edmontosaurus and Parasaurolophus, possessed one of the most sophisticated chewing mechanisms among all dinosaurs. Their jaws contained hundreds of tightly packed teeth arranged in rows, forming what is known as a dental battery. As teeth wore down from grinding tough plant material, new ones continuously replaced them from below, ensuring a perpetual grinding surface. This allowed hadrosaurs to efficiently process large quantities of fibrous plants, including conifers, cycads, and the newly evolving flowering plants. The elaborate crests on the heads of many hadrosaurs, which often contained hollow passages connected to their nasal cavities, are thought to have played a role in vocal communication, potentially signaling within herds about feeding grounds or predators. Ceratopsians, the horned dinosaurs like Triceratops and Styracosaurus, were another prominent group of Cretaceous herbivores. They possessed a sharp, parrot-like beak at the front of their mouths, which they used to snip off tough vegetation. Behind the beak, their teeth were arranged for shearing, allowing them to slice through plant material like a pair of scissors. Ceratopsians were typically low-level browsers, feeding on ferns, cycads, and other ground-level plants. Their powerful jaws and robust skulls, along with their defensive horns and frills, indicate they were well equipped to both process their food and protect themselves while foraging. Armored dinosaurs such as stegosaurs and ankylosaurs were also herbivores. Stegosaurus, with its small leaf-shaped teeth, was likely a selective browser, feeding on soft, low-growing plants. Its relatively small head and weak jaws suggest it did not consume large quantities of tough vegetation. Ankylosaurs, the heavily armoured living tanks of the Cretaceous, also had simple leaf-shaped teeth suitable for browse on softer plants. Their robust bodies and defensive armour would have allowed them to forage relatively safely in areas where predators were present. Pachycephalosaurs, the dome-headed dinosaurs, had small leaf-shaped teeth at the front of their jaws, indicating a diet of soft plants, leaves, and possibly fruits, which would have been increasingly available with the rise of flowering plants. On the other side of the dietary spectrum were the carnivorous dinosaurs, primarily represented by the theropods, the beast-footed dinosaurs. These bipedal predators were the apex hunters of their respective ecosystems, with adaptations specifically designed for capturing, killing, and consuming other animals. Tyrannosaurus rex, the iconic late Cretaceous predator, possessed a massive skull, powerful jaws, and banana-sized serrated teeth that were capable of crushing bone. Its bite force was among the strongest of any known land animal. While some debate exists about whether Tyrannosaurus rex was primarily an active hunter or a scavenger, scientific consensus suggests it was an opportunistic predator capable of both. Its large size and keen senses would have allowed it to dominate its environment. Other large theropods, such as Allosaurus from the Jurassic period, had lighter, more flexible skulls compared to tyrannosaurids. Their teeth were serrated and blade-like, ideal for slicing through flesh rather than crushing bone. Evidence from fossilized trackways and bone beds suggests that Allosaurus may have hunted in groups, allowing them to bring down larger prey, including juvenile sauropods. Spinosaurus, a unique Cretaceous theropod from North Africa, displayed highly specialized adaptations for a semi-aquatic fish-eating lifestyle. Its long, slender snout filled with conical, non-serrated teeth was well suited for catching slippery fish. Isotope analysis of its bones further supports a diet rich in aquatic prey. Smaller theropods, particularly the dromaeosaurids, often referred to as raptors, such as Velociraptor and Deinonychus, were agile and formidable predators. They possessed sharp, recurved teeth, strong grasping forelimbs with sharp claws, and a distinctive enlarged sickle-shaped claw on the second toe of each foot. This killing claw was likely used to incapacitate or disembowel prey. Evidence from fossil finds, such as Deinonychus found associated with Tenontosaurus remains, suggests that dromaeosaurids might have hunted cooperatively in packs, allowing them to overpower animals much larger than themselves. While most dinosaurs clearly fit into either herbivore or carnivore categories, some smaller species may have been omnivorous, consuming a mixed diet of plants and small animals. For example, some ornithomimids, or ostrich mimics, with their toothless beaks, are thought to have eaten plants, insects, eggs, and small vertebrates. Troodontids, with their relatively large brains and keen vision, may have also had a varied diet. The specialized teeth, jaw mechanics, and body structures of dinosaurs thus paint a vivid picture of their diverse dietary strategies, reflecting the complex ecological roles they played in the ancient world and their remarkable adaptations to the available food sources. The concept of dinosaur families extends beyond biological classification to encompass their social behaviors, how they lived in groups, and the ways they cared for their young. While the extent of social complexity varied greatly among different dinosaur species, fossil evidence provides compelling insights into cooperative living, communication, and parental investment, painting a picture of ancient reptilian societies far more intricate than once imagined. One of the most direct lines of evidence for group living among dinosaurs comes from fossilized trackways, which are preserved footprints in ancient sediments. Numerous sites around the world reveal multiple dinosaur footprints moving in the same direction, sometimes in parallel lines, indicating that animals of various sizes, including adults and juveniles, traveled together in herds. Large-scale trackways of sauropods, like those from the Jurassic Morrison Formation in North America, strongly suggest that these colossal long-necked herbivores moved in herds, possibly as a defensive strategy against large predators like Allosaurus. Similarly, extensive trackways of ornithopods, such as hadrosaurs, indicate gregarious behavior, with vast numbers of individuals moving across ancient landscapes. Further evidence for group living comes from bone beds, which are large concentrations of fossilized bones belonging to multiple individuals of the same species found together. Some bone beds contain hundreds or even thousands of individuals that appear to have died simultaneously, perhaps from a flood, drought, or volcanic eruption. For instance, mass mortality sites of Centrosaurus, a horned dinosaur in Alberta, Canada, suggest that these ceratopsians lived in large herds that occasionally succumbed to natural disasters. Such bone beds are powerful indicators of social structures, as solitary animals would not typically aggregate in such numbers at the time of death. Beyond simply living in groups, fossil evidence suggests that many dinosaurs engaged in complex social behaviors. Herding behavior, particularly among large herbivores, offered significant advantages. Safety in numbers would have been a primary benefit, as a large group could more effectively deter or confuse predators. A single individual in a herd might be vulnerable, but a group could present a formidable front or make it difficult for a predator to isolate a target. Herding also facilitated efficient foraging, allowing a large group to sweep through an area, consuming vast amounts of vegetation. This cooperative foraging may have led to migratory patterns, as herds moved between seasonal feeding grounds. Communication within dinosaur groups is largely inferred but supported by anatomical features. Many hadrosaurs, such as Parasaurolophus, possessed elaborate hollow crests on their heads. These crests were connected to their nasal passages and are thought to have functioned as resonating chambers, allowing them to produce distinctive low-frequency calls. Such calls could have been used for species recognition, signaling alarms, attracting mates, or coordinating group movements. Similarly, the elaborate frills and horns of ceratopsians, while serving defensive purposes, also varied significantly between species and individuals, suggesting they played a role in visual display, either for attracting mates or establishing dominance within a group. The display potential of brightly coloured skin or feathers, although rarely fossilised, cannot be ruled out for many dinosaurs. Intraspecific combat, or fighting among individuals of the same species, is another form of social interaction for which there is direct fossil evidence. Healed injuries on the skulls of certain dinosaurs, particularly ceratopsians and pachycephalosaurs, provide clues about their aggressive behaviours. The thickened, bony domes of pachycephalosaurs, like Pachycephalosaurus itself, are often interpreted as adaptations for headbutting contests, possibly for territorial disputes or mating rituals, much like modern-day bighorn sheep. The powerful horns and frills of ceratopsians show evidence of horn-locking and pushing contests, where individuals likely engaged in dominance displays or competed for mates. Such evidence indicates complex social hierarchies and competitive interactions within dinosaur groups. Perhaps one of the most compelling aspects of dinosaur social behaviour relates to their reproduction and parental care. All known dinosaurs laid eggs, and discoveries of fossilised eggs, nests, and even embryos have revolutionised our understanding of their breeding habits. Large nesting sites or colonies provide strong evidence for communal nesting, where multiple females would lay their eggs in close proximity. The most famous example is the Egg Mountain site in Montana, where nests of the Hadrosaur maiasaura, meaning good mother lizard, were discovered. These nests show evidence of repeated use over many years, indicating that female dinosaurs returned to the same nesting grounds. The degree of parental care in dinosaurs varied, but some species clearly invested significant effort in raising their young. In the case of Maiasaura, fossil evidence includes nests with unhatched eggs, hatchlings and juveniles, suggesting that the young remained in the nest for a period after hatching. The wear on the teeth of very young Maiasaura suggests they were not able to forage for themselves immediately, implying that parents or other adults brought food to the nest or continued to feed them. The discovery of relatively fragile eggshells and nest structures further suggests that adult Maiasaura protected their young from predators and likely provided some form of care until they were large enough to leave the nest. This level of parental investment is more akin to that seen in modern birds than in most reptiles. While extensive parental care is well documented for some ornithopods, the social behaviours and parental care of other groups are less certain. For large sauropods, due to their immense size, direct parental care beyond egg-laying might have been limited, with safety primarily found in herd numbers. However, large trackways show adults and juveniles moving together, suggesting that young sauropods were integrated into the herd for protection. For carnivorous theropods, the evidence for social behaviour, particularly pack hunting, is still debated. While some fossil assemblages and trackways might suggest cooperative hunting in groups like Deinonychus or Allosaurus, definitive proof of complex cooperative strategies, beyond simply congregating at a kill site, remains elusive. Nonetheless, the rapid growth rates inferred from bone histology in many dinosaurs suggest high metabolic rates and a need for substantial nourishment during their juvenile stages, supporting the idea of parental provisioning or a protected environment during early life. The study of dinosaur families continues to evolve, revealing new insights into the complex social lives of these ancient creatures. Earth's overall climate during the Mesozoic era, the age of dinosaurs that spanned from approximately 252 million to 66 million years ago, was profoundly different from the climate we experience today. For the vast majority of this incredibly long period, the planet was characterized by a generally warmer and more humid environment, with significantly higher atmospheric carbon dioxide levels, and, crucially, a near-complete absence of polar ice caps. This consistent warmth provided a stable and expansive habitat that supported the evolution and incredible diversity of dinosaur life across nearly every continent. The Triassic period, the earliest phase of the Mesozoic, began in the aftermath of the Permian-Triassic extinction event, which had dramatically reshaped Earth's ecosystems. Geologically, the Triassic was dominated by the supercontinent Pangaea, a single, massive landmass that stretched from pole to pole. This continental configuration had a defining influence on the climate. The immense size of Pangaea meant that oceanic influences were limited, leading to a largely continental climate. The interior of the supercontinent experienced extreme temperatures, with very hot, arid conditions during the day and significant temperature drops at night. Evidence for this aridity comes from extensive deposits of evaporites, such as rock salt and gypsum, which form in dry evaporating basins. Coastal regions, however, were subject to strong monsoonal patterns, bringing intense seasonal rainfall. This dry-wet seasonality was a defining characteristic of the Triassic, affecting the types of vegetation and animals that could thrive. As the Mesozoic progressed into the Jurassic period, starting around 201 million years ago, Pangaea began to rift apart. The initial rifting accelerated, leading to the gradual separation of the northern continents, Laurasia, from the southern continents, Gondwana. This continental drift led to the formation of a new ocean basins and a general increase in oceanic circulation, which brought more moisture to continental interiors. Consequently, the Jurassic climate was generally more humid and less arid than the Triassic, although it remained consistently warm. Vast shallow seas formed across continental landmasses, contributing to a more stable and widespread warm environment. Evidence for this humid warmth comes from extensive coal deposits, which indicate widespread lush vegetation and swampy conditions. The warm, humid climate of the Jurassic supported the proliferation of vast conifer and cycad forests, providing an abundant food supply for the newly evolving gigantic sauropods. The Cretaceous period, from 145 million to 66 million years ago, saw the continued and rapid breakup of the continents, moving them towards their modern positions. South America and Africa began to separate definitively. India drifted northward towards Asia, and North America and Eurasia continued to split. This increasing fragmentation of land masses led to more distinct regional climates and increased oceanic influence across the globe. Despite this fragmentation, the Cretaceous remained largely a warm period, with global average temperatures significantly higher than today. Sea levels were also at their highest during the Cretaceous, with extensive epicontinental seas flooding large portions of continents, such as the Western Interior Seaway that bisected North America. This high sea level and increased coastal areas likely contributed to the overall warmth and humidity. Evidence for this sustained Mesozoic warmth comes from multiple lines of geological and paleontological data. The global distribution of large, cold-blooded reptiles like crocodiles and turtles in areas that are now high latitudes indicates that polar regions were much warmer and lack the ice caps we see today. Fossilized plant remains, such as those of ferns, cycads, and warmth-loving conifers, are found in regions that are currently temperate or cold, further supporting the idea of a widespread warm climate. Stable isotope ratios in fossilized bones, teeth, and marine shells can also provide insights into ancient temperatures, consistently pointing to warmer global conditions throughout much of the Mesozoic. For instance, oxygen isotope analysis of dinosaur bones from high latitudes suggests that these animals lived in mild, frost-free environments. Several key factors contributed to Earth's consistently warm Mesozoic climate. Foremost among them was continental drift, or plate tectonics. The changing configuration of continents influenced ocean currents, which distribute heat around the globe. When continents are arranged in a way that allows warm currents to flow more freely, global temperatures tend to rise. Furthermore, intense volcanic activity, often associated with the rifting of continents and the formation of new ocean crust, played a critical role. Large igneous provinces, such as the Central Atlantic Magmatic Province that formed during the Triassic-Jurassic transition, and the Deccan Traps at the end of the Cretaceous, released massive quantities of greenhouse gases, particularly carbon dioxide, into the atmosphere. Atmospheric carbon dioxide levels during the Mesozoic were significantly higher than modern pre-industrial levels, ranging from several hundreds to thousands of parts per million. This elevated concentration of greenhouse gases created a stronger greenhouse effect, trapping more heat in the atmosphere and contributing to the sustained global warmth. The absence of major continental ice sheets also meant that more of the sun's energy was absorbed by Earth's surface rather than being reflected by ice, further contributing to higher temperatures. This warm and humid ancient climate had a profound impact on dinosaur life. The widespread availability of lush vegetation, supported by ample warmth and moisture, provided an abundant food supply that could sustain enormous herbivorous dinosaur populations. This rich food source, in turn, allowed for the evolution of the gigantic sizes seen in sauropods and other large plant eaters. The consistent warmth may have also played a role in the metabolic rates of dinosaurs, potentially allowing them to maintain higher activity levels without expending as much energy on thermoregulation as animals in colder climates. Furthermore, the mild conditions, even in what are now polar regions, meant that dinosaurs could inhabit vast areas of the planet, leading to their global distribution. The lack of extreme seasonal temperature shifts, such as harsh winters, might have reduced the need for hibernation or extensive long-distance migrations for many dinosaur species, allowing them to remain active year-round. The long-term stability of this warm Mesozoic climate provided a critical backdrop for the incredible evolutionary success and diversification of dinosaurs over millions of years. The end of the dinosaur age, a profound turning point in Earth's history, is marked by a distinctive geological layer known as the KPG boundary. This specific moment in time, approximately 66 million years ago, represents a dramatic and sudden shift in life on our planet. For many years, this boundary was referred to as the KT boundary, standing for Cretaceous Tertiary. However, modern geological terminology has replaced tertiary with Paleogene for greater precision in classifying geological periods. Thus, the boundary is now officially designated as the Cretaceous Paleogene, or KPG boundary. It serves as the definitive dividing line between the Mesozoic era, the age of reptiles including the non-avian dinosaurs, and the Cenozoic era, the age of mammals. This KPG boundary is not merely a theoretical concept. It is a tangible, physical layer of sediment found in rock formations around the world. From deep ocean sediments to exposed rock faces on land, geologists have identified this thin, distinctive stratum, which typically measures from a few millimeters to several centimeters in thickness. Its global presence and unique composition make it an extraordinary marker of a catastrophic event that simultaneously affected nearly every corner of the Earth. The discovery and subsequent intensive study of this boundary layer provided the foundational evidence that revolutionized our understanding of how the dinosaurs, and countless other life forms, vanished so abruptly. One of the most striking characteristics of the KPE boundary layer is its unusually high concentration of the element iridium, known as the iridium anomaly. Iridium is extremely rare in Earth's crust, as most of it sank to the planet's core during its formation. However, iridium is far more common in extraterrestrial objects like meteorites and asteroids. The discovery of a worldwide iridium-rich layer at the KPG boundary in 1979 by Luis Alvarez and his son Walter Alvarez provided the first strong clue that an extraterrestrial impact might have caused the mass extinction. The iridium layer is found in sediments from Denmark to New Zealand, from North America to China, consistently marking the same geological moment. Its presence pointed strongly towards a cosmic source, as no known terrestrial volcanic activity could have distributed iridium in such a uniformly global pattern. In addition to the iridium anomaly, the KPG boundary layer contains several other telltale signs of a colossal impact event. One such indicator is the presence of shocked quartz. Quartz grains are common minerals in Earth's crust, but under normal geological processes, they do not exhibit certain types of deformation. Shocked quartz, however, displays distinctive microscopic parallel lamellae, or planar deformation features, within its crystal structure. These features are formed only by the passage of extremely powerful shock waves, such as those generated by a hypervelocity impact or a nuclear explosion. The widespread occurrence of shocked quartz within the KPG layer provides undeniable evidence of an immense sudden burst of energy, far beyond anything produced by volcanic eruptions. Another crucial component found within the KPG boundary are microtectites, also known as spherules. These are tiny, often microscopic glass beads that are formed when terrestrial rock is superheated by an impact event, melts, and is then ejected into the atmosphere. As this molten rock rapidly cools during its ballistic flight, it solidifies into small glassy spheres before raining back down to Earth. The global distribution of these microtectites within the KPG layer is consistent with material ejected from a massive impact site, spreading across continents and oceans. Their presence signifies the immense scale of the impact, capable of generating enough energy to melt vast quantities of rock and distribute it globally. Beyond the direct evidence of an impact, the KPG boundary layer also contains geological signatures of the immediate aftermath. A global soot layer is often found within or just above the iridium-rich layer. This soot is interpreted as evidence of massive, widespread wildfires that ignited across the planet following the impact. The immense energy released by the impactor, combined with superheated ejecta raining back down, would have ignited vegetation over vast areas, creating a global firestorm. The resulting smoke and ash would have further darkened the skies, contributing to the environmental catastrophe. Furthermore, in coastal regions, geological formations at the KPG boundary often include tsunami deposits. These are layers of disrupted sediment, sometimes containing large boulders and mixed marine and terrestrial fossils that can only be explained by the passage of colossal waves. The presence of these deposits, particularly prominent around the Gulf of Mexico, points to an impact that occurred in or near an ocean basin, generating tsunamis of unprecedented scale that inundated ancient coastlines for thousands of miles. The significance of the KPG boundary lies not only in its unique composition, but also in what it signifies for the history of life. The rock layers immediately below the KPG boundary are rich in dinosaur fossils, as well as ammonites, marine reptiles, and many other groups characteristic of the Mesozoic era. In stark contrast, the layers immediately above the boundary show a dramatic and sudden absence of these characteristic Mesozoic life forms. Dinosaur fossils vanish, ammonites disappear entirely, and many other groups suffer severe losses, replaced by an ecosystem dominated by different species, particularly mammals, which rapidly diversified in the Paleogene. This abrupt faunal turnover at the boundary indicates that the extinction event was not a gradual decline but a sudden catastrophic collapse of ecosystems on a global scale. The KPG boundary thus serves as a tangible geological testament to the end of an era, marking the precise moment when the age of dinosaurs concluded and a new chapter in Earth's biological history began. For centuries, the disappearance of the dinosaurs remained one of the greatest mysteries in natural history. Various theories, ranging from climate change and disease to volcanic eruptions and rising sea levels, were proposed to explain their sudden vanishing at the end of the Cretaceous period. However, in the late 20th century, a revolutionary new hypothesis emerged, presenting a compelling and now widely accepted explanation: the impact of a very large space rock hitting Earth. This idea, first proposed by Nobel laureate physicist Luis Alvarez and his geologist son Walter Alvarez in 1980, fundamentally shifted scientific understanding of mass extinctions. The genesis of the asteroid impact hypothesis came from the discovery of the iridium anomaly in the KPG boundary layer. As described previously, iridium is incredibly rare in Earth's crust but relatively common in extraterrestrial objects. When the Alvarez team found a sharp, anomalous spike in iridium concentration at the KPG boundary clay in Gubbio, Italy, and subsequently confirmed it at other sites globally, they realized that the most plausible explanation for this worldwide signature was the impact of an asteroid or comet. This discovery provided the first strong physical evidence linking an extraterrestrial event to a major extinction. The main idea posits a dramatic and rapid sequence of events triggered by this cataclysmic impact. When a colossal asteroid or comet, estimated to be several miles in diameter, slammed into Earth, it released an unimaginable amount of energy. The force of this impact would have been equivalent to billions of times the energy of the atomic bomb dropped on Hiroshima, or roughly 100 million megatons of TNT. This immense energy instantly vaporized the impactor and vast quantities of Earth's crust at the point of collision, creating an enormous fireball and generating a colossal shockwave that propagated globally. The immediate aftermath of the impact would have been devastating, particularly near the impact site. A massive explosion would have ejected superheated rock and debris, including microtectites and shocked quartz, high into the atmosphere and even into low Earth orbit. As this ejector re-entered the atmosphere, it would have rained down globally as incandescent projectiles, igniting massive, widespread wildfires across continents. The evidence for these global firestorms is found in the widespread soot layer within the Capege boundary. The intense heat from this re-entry would have caused immediate and widespread loss of life for any animals exposed on the surface. Following the initial fiery deluge, the long-term environmental consequences would have unfolded. The sheer volume of dust, ash and soot injected into the atmosphere from the impact and the global wildfires would have created a dense, opaque cloud. This cloud would have blocked out sunlight for months, or even several years, plunging the Earth into a period of prolonged darkness. With the sun's energy unable to reach the surface, photosynthesis, the process by which plants convert sunlight into energy, would have largely ceased. This sudden and sustained interruption of photosynthesis would have caused a catastrophic collapse of terrestrial and marine food chains. Plants, the base of nearly all ecosystems, would have died off, leading to the starvation of herbivorous animals, which in turn would lead to the starvation of carnivorous animals. Further atmospheric effects would have exacerbated the crisis. The impactor, if it hit a sulfur-rich area, which the Chicxulub site was, would have released enormous quantities of sulfur dioxide and other gases into the atmosphere. These gases would have combined with water vapour to form sulfuric acid aerosols. When these aerosols rained down, they would have caused global acid rain, severely damaging land vegetation and acidifying the surface layers of the oceans. Ocean acidification would have been particularly devastating for marine organisms that rely on calcium carbonate to build their shells and skeletons, such as plankton, mollusks and corals, further disrupting marine food webs. The global cooling caused by the sun-blocking dust cloud is often referred to as impact winter. Temperatures would have plummeted worldwide, leading to freezing conditions even in typically warm regions. This rapid and dramatic shift in climate, coupled with the collapse of food sources and acid rain, created an uninhabitable environment for many species that were not adapted to such sudden and extreme changes. Large animals, requiring substantial amounts of food, and those at the top of long food chains, were particularly vulnerable to this cascade of environmental disasters. The asteroid impact theory stands in stark contrast to earlier, more gradual explanations for the dinosaur extinction, such as slow climate change, widespread disease epidemics, or a gradual decline in sea levels. While these factors may have played some role in the overall pressures on Mesozoic life, they do not account for the suddenness and global synchronization of the extinction event as recorded in the KPG boundary layer. The overwhelming body of evidence, including the iridium anomaly, shocked quartz, microtectites, soot layers, tsunami deposits, and critically, the discovery of the colossal Chicxulub crater in the Yucatan Peninsula of Mexico, has solidified the asteroid impact as the leading scientific theory for the dinosaur extinction. This theory highlights the profound vulnerability of Earth's ecosystems to extraterrestrial events, and serves as a powerful reminder of the planet's dynamic history. The scientific consensus regarding the extinction of the non-avian dinosaurs 66 million years ago points to a single, catastrophic event, the impact of an exceptionally large space rock. This celestial body, whether an asteroid or a comet, possessed specific characteristics that, combined with its impact location, unleashed an unimaginable destructive force that irrevocably altered Earth's ecosystems. Understanding the nature of this impactor is crucial to comprehending the scale of the global disaster it initiated. Based on extensive geological and geophysical evidence, including the size of the Chicxulub crater and the global distribution of ejecta, scientists estimate the size of this ancient space rock to have been approximately 7 to 9 miles, or about 10 to 15 kilometers, in diameter. To put this into perspective, This is larger than Mount Everest, the tallest mountain on Earth, and significantly wider than many major metropolitan areas. An object of this size, travelling at immense speeds, possesses an extraordinary amount of kinetic energy, the energy of motion, which was converted into destructive power upon impact. The composition of the space rock is inferred from the chemical signatures found in the KPG boundary layer. The presence of elevated iridium levels globally strongly suggests an extraterrestrial origin, as iridium is far more abundant in meteorites than in Earth's crust. While it's difficult to definitively determine if the impactor was a stony asteroid or a comet, a mixture of ice and rock, the evidence generally leans towards a carbonaceous chondrate asteroid, a type of stony meteorite. This is supported by the discovery of other unusual elements and minerals at the boundary, such as chromite and nickel-rich spinel, which are also common in certain types of meteorites. Although a comet cannot be entirely ruled out, the overall geological signature aligns well with the stony asteroid. The speed at which this colossal object impacted Earth was truly incredible. Asteroids and comets typically travel through space at velocities far exceeding anything experienced on Earth. When an object this large encounters Earth's gravitational pull, it accelerates further. The impactor is estimated to have struck Earth at a staggering speed of at least 40,000 miles per hour, or approximately 20 kilometers per second. At this hypersonic velocity, the object's mass became an instrument of unimaginable destruction. The kinetic energy released upon impact was equivalent to billions of atomic bombs, or roughly 100 million megatons of TNT, making it the most powerful known impact event in Earth's history in the last half-billion years. The precise location of the impact was also a critical factor in the global catastrophe. The asteroid slammed into a shallow sea near what is now the Yucatan Peninsula in Mexico, creating the vast Chicxulub crater. This particular impact site was not just any location. It contained substantial deposits of sulfur-rich evaporate rocks, such as gypsum. When the asteroid struck these rocks, it not only vaporized them but also ejected enormous quantities of sulfur into the atmosphere. This sulfur, in the form of sulfur dioxide, reacted with water vapor to form vast clouds of sulfuric acid aerosols. These aerosols were highly efficient at blocking sunlight and also led to severe global acid rain, significantly exacerbating the environmental damage beyond what a similar impact on, say, granite bedrock would have caused. Impacts of this magnitude are extremely rare events in Earth's geological history. Scientists estimate that an impactor of 7 to 9 miles in diameter strikes Earth only once every 50 to 100 million years. This rarity underscores the unique and catastrophic nature of the KPG event, differentiating it from more common, smaller meteorite impacts that occur regularly. The fortuitous combination of a very large object and a particularly hazardous impact site created a perfect storm for mass extinction. The immediate physical effects of such an impact would have been devastating beyond comprehension. Upon striking, the space rock would have excavated a transient crater tens of miles wide and several miles deep within mere seconds. The immense pressure and heat generated would have instantly vaporized vast quantities of rock from both the impactor and the target site, creating a colossal plume of superheated material that rose far above the atmosphere. This ejector would have then fallen back to Earth globally as molten droplets, microtectites, and superheated debris, causing the global wildfires. The impact would have generated a global seismic shockwave, triggering massive earthquakes and potentially widespread volcanic activity far from the impact site. A massive tsunami, hundreds or even thousands of feet high, would have radiated outwards from the impact point, inundating ancient coastlines thousands of miles away. The specific characteristics of this one space rock, its immense size, its high velocity, and its unfortunate impact location, converged to create a chain of events that culminated in the most significant mass extinction of the last 66 million years, forever changing the course of life on Earth. Following the asteroid's catastrophic impact and the immediate terrifying fireball, the Earth was swiftly engulfed in a secondary but equally devastating environmental catastrophe: global wildfires. This widespread conflagration was not a localized event but a planetary phenomenon, ignited by the intense heat and the raining down of incandescent debris ejected from the Chicxulub impact site. The evidence for these immense fires is preserved in a distinct layer of soot and charcoal found within the Cretaceous-Paleogene boundary layer across the globe. The primary mechanism for the ignition of these global wildfires was the rain of fire described as part of the immediate aftermath. As the superheated ejecta, consisting of microtectites and other pulverized rock particles, re-entered Earth's atmosphere at incredibly high speeds, atmospheric friction heated these fragments to incandescent temperatures, often thousands of degrees Celsius. This glowing material then fell across virtually the entire planet, igniting any flammable organic material it touched. It would have been akin to billions of tiny superhot meteorites, simultaneously striking the Earth's surface over a matter of hours or days, depending on the speed and distribution of the ejecta. Beyond direct contact, the intense radiant heat generated by this re-entering ejecta may have been sufficient on its own to cause spontaneous combustion of vegetation, even without direct impact from the fiery particles. The atmosphere itself would have been superheated by the sheer volume of re-entering material, creating a global thermal pulse that cooked the surface of the Earth. Any dry vegetation, vast forests, grasslands, and even peat deposits would have instantly burst into flames. The most compelling evidence for these global wildfires is the widespread discovery of a distinct layer of soot and charcoal found precisely at the KPG boundary. This soot, composed of carbonized plant material and other organic residues, is found in geological sections across every continent, including marine sediments where soot would have settled after being carried by wind and currents. The sheer volume of soot present in this layer indicates that an immense amount of biomass, likely a significant portion of Earth's terrestrial vegetation, burned during this event. Scientific analysis of the chemical composition of this soot, specifically the presence of particular polycyclic aromatic hydrocarbons, confirms that it originated from the large-scale burning of organic matter, consistent with massive forest fires. The scale of these fires would have been immense. It is estimated that a substantial percentage, possibly as high as 70%, of Earth's terrestrial biomass could have been consumed in these infernos. Forests would have been consumed in raging firestorms, grasslands would have been reduced to ash, and even peat swamps and lignite beds would have ignited. These fires would have raged for days or even weeks, transforming vast landscapes into scorched wastelands. The intense heat would have killed any animals that could not find shelter deep underground or underwater. The environmental consequences of these global wildfires extended far beyond the immediate destruction of life and habitat. The massive amounts of smoke, ash, and particulate matter released into the atmosphere by these fires would have significantly contributed to the global dust cloud initiated by the impact itself. This dense atmospheric veil would have further blocked out sunlight, exacerbating the impact winter and prolonging the period of darkness that crippled photosynthesis and collapsed global food chains. The fires also released vast quantities of greenhouse gases, such as carbon dioxide, into the atmosphere. While initially overshadowed by the cooling effect of the dust, this carbon dioxide would later contribute to a subsequent period of global warming once the dust cleared. Furthermore, the destruction of vegetation covered by the fires would have led to long-term ecological damage. Without plants to hold the soil, widespread erosion would have occurred. The removal of the primary producers from the base of the food web would have had cascading effects, severely disrupting the ecosystems that managed to survive the initial impact. The global wildfires were not just a consequence of the asteroid impact. They were an integral part of the interconnected chain of environmental disasters that collectively contributed to the mass extinction event, pushing many species beyond their capacity to survive and transforming the planet on an unprecedented scale. The compelling scientific narrative of the dinosaur extinction reached a pivotal moment with the discovery and confirmation of the impact site, the colossal Chicxulub crater. This geological feature, predominantly hidden beneath the Yucatan Peninsula in Mexico and extending into the waters of the Gulf of Mexico, serves as the definitive smoking gun that provided irrefutable proof for the asteroid impact theory. Its unearthing in the late 1970s and early 1990s cemented the understanding that an extraterrestrial collision was the primary cause of the end Cretaceous mass extinction. The Chicxulub crater is one of the largest confirmed impact structures on Earth. Its sheer size is staggering, with an estimated diameter of approximately 112 miles, or about 180 kilometres. To put this in perspective, this is a width greater than the distance from London to Bristol in the United Kingdom, or roughly the length of the entire country of Belgium. Such a massive structure is indicative of an impactor of truly colossal scale, consistent with the estimated 7 to 9 mile asteroid. Despite its immense size, the Chicxulub crater remained largely undiscovered for decades because it is not visible on the surface. Most of the crater is buried beneath layers of younger sedimentary rocks, some reaching depths of up to 1 kilometre, effectively concealing it from direct observation. The initial clues to its existence emerged in the 1970s, when Antonio Camargo and Glenn Penfield, geophysicists working for the Mexican national oil company Pemex, conducted oil exploration surveys in the Yucatan. Their gravitational and magnetic field anomaly maps revealed a massive, distinct circular pattern. However, at the time, their findings were primarily interpreted within the context of petroleum geology, and its significance as an impact structure was not fully recognized or widely disseminated within the broader scientific community. It was not until the early 1990s that scientific research, driven by the search for the impact site predicted by the Alvarez hypothesis and the global iridium anomaly, unequivocally identified the Chicxulub structure as the Cretaceous Paleogene impact crater. This confirmation was based on a confluence of compelling evidence gathered through various geological techniques, including drill cores taken from within and around the buried structure. One of the key pieces of evidence from these drill cores was the presence of shocked quartz. As detailed previously, shocked quartz grains exhibit microscopic deformations caused by extreme pressures, far beyond what any volcanic eruption could generate. Their discovery within the buried structure and in widespread ejecta layers around the Gulf of Mexico provided direct proof of a hypervelocity impact. Along with shocked quartz, the drill cores also reveal the telltale iridium anomaly, microtectites, tiny glass spherules formed from melted rock ejected during impact, and other minerals characteristic of extraterrestrial objects, precisely matching the global KPG boundary layer. Further geophysical surveys provided more detailed insights into the crater's buried architecture. Gravity and magnetic anomalies continued to reveal the crater's distinctive circular structure and subsurface characteristics, such as the presence of impact-melted rock. Seismic reflection surveys, which use sound waves to create images of subsurface geological structures, clearly depicted the crater's complex morphology. This morphology includes a central peak ring, a distinctive feature of very large impact craters, which forms when the ground immediately beneath the impact rebounds and then collapses, creating a ring of uplifted crust within the main crater basin. The presence of such a peak ring was definitive proof of an impact of immense energy. Beyond the direct evidence from the crater itself, the impact at Chicxulub also left clear signatures in the surrounding region and beyond. Extensive geological evidence of colossal tsunamis is found along the ancient coastlines of the Gulf of Mexico and the Caribbean, with deposits of jumbled marine and terrestrial sediments and large boulders. These tsunami deposits can be traced back to a single point of origin, the Chicxulub impact site, indicating that the impact generated waves of truly unprecedented scale that inundated vast coastal areas. The specific location of the Chicxulub impact, a shallow marine environment overlying substantial deposits of sulfur-bearing rocks like gypsum and anhydrite, was a critical factor in amplifying the global environmental catastrophe. When the asteroid struck these particular rocks, the immense heat and pressure instantly vaporized not only the asteroid itself and portions of the Earth's crust, but also the vast quantities of sulfur contained within the sedimentary layers. This vaporization released colossal amounts of sulfur dioxide and other sulfur aerosols directly into the atmosphere. These sulfur compounds formed dense stratospheric clouds that were far more effective at blocking sunlight and cooling the planet than mere dust or soot. They also led to the formation of highly corrosive sulfuric acid rain, which devastated terrestrial ecosystems and acidified the surface layers of the oceans, contributing significantly to the mass extinction of marine life. An impact of the same size on, for example, granite bedrock in a deep ocean basin, while still devastating, would likely not have released the same volume of climate-altering sulfur aerosols, potentially resulting in a less severe global environmental cataclysm. The discovery and comprehensive study of the Chicxulub crater transformed the dinosaur extinction from a geological mystery into a well-understood scientific event, demonstrating the power of extraterrestrial forces to reshape life on Earth. The asteroid's final approach to Earth, a silent cosmic bullet hurtling through space, culminated in a terrifying sequence of events that unfolded in mere seconds to minutes. As the space rock, estimated to be about 7 to 9 miles in diameter, plunged into Earth's atmosphere, it did so at an incredible hypersonic speed, likely exceeding 40,000 miles per hour. This rapid entry compressed the air in front of it, generating a superheated plasma trail and creating a deafening roar that would have been the last sound many creatures heard. The air resistance rapidly increased the temperature of both the asteroid and the surrounding atmosphere to incandescent levels, turning the incoming object into a blinding streak of light across the sky. The very first infinitesimal moment of contact between the asteroid and Earth's surface marked the beginning of an unprecedented catastrophe. Upon impact, the immense kinetic energy stored within the fast-moving asteroid was instantaneously converted into heat, light, and mechanical energy. The force released was equivalent to an explosion of approximately 100 million megatons of TNT, a power scale almost incomprehensible, far exceeding the combined destructive power of all nuclear weapons on Earth. This energy was so immense that it instantly vaporized not only the asteroid itself, but also a colossal volume of Earth's crust, forming a superheated mixture of rock, water, and gases. The immediate manifestation of this energy release was a blinding flash of light, unimaginably brighter than the sun. This incandescent flash would have been visible across continents, potentially even from the opposite side of the globe if atmospheric conditions allowed. Any creature caught in its direct line of sight within hundreds of miles would have been instantly incinerated or suffered immediate and permanent blindness. Following this searing flash, a rapidly expanding fireball of superheated vaporized rock and plasma erupted from the impact site. This fireball, quickly growing to hundreds of miles in diameter, ascended rapidly into the atmosphere, carrying with it pulverized and melted terrestrial material. Temperatures within this rapidly expanding plasma cloud would have reached thousands of degrees Celsius, creating an inferno at the heart of the explosion. Simultaneously with the fireball's expansion, a colossal shockwave was generated, propagating outwards both through the ground and through the atmosphere. The ground shockwave was equivalent to an earthquake of magnitude 10 or 11, a scale rarely, if ever, seen in modern times. This seismic shockwave would have reverberated across the entire planet, causing massive tectonic plate movements, triggering widespread fault slippage, and potentially unleashing volcanic activity far from the impact site. Animals across continents would have been thrown off their feet, and the landscape would have rippled violently. The atmospheric shockwave was equally, if not more, destructive. Initially travelling at supersonic speeds, this powerful blast wave would have flattened everything in its path for hundreds, even thousands, of miles from ground zero. Trees would have been instantly ripped from the ground and flung great distances, forests annihilated, and any standing structures obliterated. Animals caught in this initial blast would have been crushed, thrown, or disintegrated. The force was so immense that it would have stripped foliage from trees, scoured the landscape bare, and initiated a wave of devastation radiating outwards at incredible speeds. As the fireball expanded and excavated the Chicxulub crater, vast quantities of superheated rock and debris were ejected upwards and outwards at hypervelocity, forming what is known as an ejector curtain. This material, consisting of vaporized rock, molten droplets, microtectites, and shattered rock fragments, including shocked quartz, rose high into the atmosphere and even breached into low Earth orbit. Within minutes, this incandescent ejector began to re-enter the atmosphere globally. The friction generated by their re-entry would have heated these particles to white-hot temperatures, causing them to glow intensely. This rain of fire, as it has been metaphorically described, would have blanketed the entire planet, raining down billions of superheated projectiles onto the Earth's surface. The immediate devastation within the immediate blast zone of the impact was absolute, with all life vaporized or instantly incinerated. This terrifying cascade of events, from the blinding flash to the earth-shaking shockwave and the global rain of fire, unfolded in a mere matter of seconds to minutes, instantaneously transforming the Cretaceous world into a planetary inferno. Following the catastrophic asteroid impact and the ensuing global wildfires, Earth was plunged into a period of profound dust and darkness. This atmospheric veil, consisting of immense amounts of pulverized rock, soot, and chemical aerosols, became a primary driver of the mass extinction, blocking out the sun and crippling the very foundation of life on the planet. The origin of this atmospheric loading can be traced directly back to the initial impact and its immediate environmental consequences. The first major source of material injected into the atmosphere was the asteroid impact itself. When the 7 to 9 mile wide space rock struck the Earth, it pulverized vast quantities of rock from the impact site. This included not only the asteroid material but also tens of thousands of cubic miles of terrestrial rock, which were vaporized, melted, and fragmented. A significant portion of this material was ejected high into the atmosphere, much of it as fine dust particles micrometers in size. This fine dust, along with larger ejecta like microtectites and shocked quartz, was propelled far above the stratosphere, some reaching into the mesosphere or even beyond Earth's immediate atmosphere. The second critical source was the widespread global wildfires that erupted immediately after the impact. As described previously, these fires consumed vast amounts of terrestrial vegetation, releasing enormous quantities of soot and ash into the atmosphere. This soot, composed of carbonized organic matter, contributed millions of tons of light-absorbing particles to the already dust-laden sky. The sheer scale of these fires ensured that this soot was a global phenomenon, blanketing the planet. Crucially, the Chicxulub impact site's unique geology added a third, particularly devastating component to the atmospheric veil: sulfur aerosols. The asteroid struck a region of shallow marine sediments rich in sulfur-bearing evaporate rocks, such as gypsum and anhydrite. The immense energy of the impact instantly vaporized these sulfur-rich rocks, injecting colossal amounts of sulfur dioxide and other sulfur compounds directly into the upper atmosphere. Once in the stratosphere, these sulfur gases reacted with water vapor to form tiny droplets of sulfuric acid, creating a dense layer of aerosols. Unlike dust and soot, which settle relatively quickly, these fine sulfuric acid aerosols can remain suspended in the stratosphere for several years, effectively blocking incoming solar radiation for an extended period. Once in the upper atmosphere, these dust, soot, and sulfur particles were rapidly dispersed around the entire globe by high-altitude winds, creating a thick, opaque cloud that enveloped the planet within days or weeks. This atmospheric veil acted as a colossal sunshade, preventing a substantial portion of the sun's energy from reaching Earth's surface. The immediate and most critical consequence of this prolonged darkness was the near-total cessation of photosynthesis. Plants, the primary producers at the base of nearly all terrestrial and marine food chains, rely on sunlight to convert carbon dioxide and water into energy. Without sufficient sunlight, these plants would have been unable to grow, or would have died off completely, particularly in the surface waters of the oceans where phytoplankton forms the base of the marine food web. The duration of this darkness is estimated to have been significant. The initial, most severe phase of darkness, with light levels potentially too low for any photosynthesis, could have lasted for several months. A substantial reduction in sunlight, still crippling to most plant life, might have persisted for several years as the fine particles slowly settled out of the atmosphere. Even a brief period of total darkness would be catastrophic for most ecosystems, but a prolonged period would ensure widespread collapse. The consequences of this prolonged darkness were dire. The direct death of plants due to starvation from lack of sunlight initiated a cascading collapse of food chains. Herbivorous dinosaurs and other plant eaters would have quickly run out of food and starved. Their demise, in turn, would have led to the starvation of carnivorous dinosaurs and other predators who relied on herbivores for sustenance. Even organisms not directly killed by the impact, fires, or tsunamis would have succumbed to the subsequent lack of food. The disruption extended to marine ecosystems, where the death of phytoplankton led to the collapse of zooplankton and consequently larger marine life. The plunge into darkness was thus a fundamental environmental shift that choked off the energy supply to Earth's ecosystems, proving to be one of the most lethal aspects of the post-impact world. The profound dust and darkness that enveloped Earth following the asteroid impact directly led to a period of extreme global cooling, a phenomenon scientifically termed impact winter. This long period of intense cold, combined with the lack of sunlight, created an uninhabitable environment for many species, particularly large dinosaurs and those sensitive to temperature fluctuations. The mechanism behind this drastic temperature drop was the effective blockage of solar radiation from reaching Earth's surface. As vast quantities of pulverized rock dust, soot from global wildfires, and particularly sulfur aerosols filled the stratosphere, they formed a dense atmospheric veil. This veil acted like a colossal blanket, but instead of trapping heat in, it reflected incoming sunlight back into space. With the sun's energy prevented from warming the planet's surface, global average temperatures plummeted rapidly. Climate models simulating the effects of such an atmospheric loading suggest that temperatures could have dropped by tens of degrees Celsius within weeks of the impact, reaching freezing levels even in typically warm tropical and subtropical regions. The initial, most severe phase of this impact winter is estimated to have lasted for several months, potentially up to a year. During this period, conditions would have been analogous to a perpetual, extremely harsh winter across the entire globe. Even areas that never experience freezing temperatures today would have been subjected to sub-zero conditions. Following this initial intense cold, a more moderate but still significantly cooler period would have persisted for several years as the finer particles and sulfur aerosols slowly settled out of the stratosphere. The recovery to pre-impact temperatures would have been a gradual process, taking many years. The consequences of this extreme cold were catastrophic for life. Terrestrial plants, already suffering from the lack of sunlight, would have succumbed en masse to the freezing temperatures. Plants sensitive to frost, which would have constituted a large portion of the Mesozoic flora, adapted to a generally warm climate, would have died off rapidly. Even hardy species would have struggled to survive the combined assault of darkness and cold. This massive die-off of vegetation on land eliminated the food source for herbivorous dinosaurs and many other plant-eating animals. Aquatic ecosystems were also severely impacted. The surface waters of oceans and large lakes would have cooled rapidly, potentially freezing over in higher latitudes and even experiencing significant cooling in tropical regions. This sudden temperature drop would have devastated plankton communities, which are highly sensitive to changes in temperature and light. The collapse of phytoplankton, the primary producers in marine environments, would have starved the zooplankton that fed on them, leading to a cascading collapse of the entire marine food web. Fish, marine reptiles, and other aquatic life that depended on this food web would have perished from starvation or the physiological stress of the cold. The interplay between the prolonged darkness and the extreme cold was mutually reinforcing and devastating. The darkness prevented plants from photosynthesizing, while the cold killed off any plants that might have otherwise survived. Large animals, including most non-avian dinosaurs, were particularly vulnerable to impact winter. Their enormous bodies required vast amounts of food daily, and their large surface area meant they lost heat quickly in freezing conditions. Unlike smaller animals, they could not easily burrow underground or find insulated shelters. Their high metabolic demands meant they would succumb to starvation much faster than smaller creatures with lower energy needs. Differential survival during impact winter favoured certain groups. Small animals, including early mammals, some birds and amphibians, often had the ability to burrow underground, find shelter in caves, or enter states of torpor, allowing them to escape the worst of the cold and dark. Scavengers that could find dead organic matter and animals with lower metabolic rates that could survive longer without food also had an advantage. While the initial impact, fires and tsunamis caused immense immediate destruction, it was the prolonged global climate catastrophe of impact winter, the pervasive cold and darkness, that ultimately delivered the killing blow to the majority of life forms, particularly the large non-avian dinosaurs, marking a decisive end to their long reign. The catastrophic asteroid impact at the end of the Cretaceous period, approximately 66 million years ago, unleashed a complex series of environmental disasters, one of which was the widespread formation of highly acidic rain. This corrosive precipitation, far more intense and widespread than anything seen in modern times, severely damaged terrestrial plants and acidified aquatic environments, contributing significantly to the mass extinction event. The chemicals responsible for this acid rain originated from two primary sources: the vaporization of sulfur-rich rocks at the impact site and the atmospheric effects of the immense energy released by the collision. The most significant contributor to the acid rain was the vaporization of sulfur-bearing rocks at the Chicxulub impact site. The asteroid struck a shallow marine platform in the Yucatan Peninsula that contained vast deposits of evaporate minerals, specifically gypsum and anhydrite. These minerals are rich in sulfur. When the 7 to 9 mile wide asteroid slammed into this particular geological formation, the immense heat and pressure instantly vaporized a colossal volume of these sulfur-rich rocks. This process injected an enormous quantity of sulfur dioxide gas directly into the upper atmosphere, specifically the stratosphere. Once in the stratosphere, sulfur dioxide rapidly reacts with water vapor and other atmospheric chemicals to form tiny droplets of sulfuric acid, creating a dense layer of sulfuric acid aerosols. These aerosols are highly effective at reflecting sunlight back into space, contributing to the impact winter, but they also serve as the primary source of acid rain. A secondary, though still significant source of chemicals contributing to acid rain was the intense heat generated by the impact itself and the subsequent global wildfires. The sheer energy of the asteroid striking the atmosphere and Earth's surface would have superheated the air, causing atmospheric nitrogen and oxygen to combine and form large quantities of nitrogen oxides. These nitrogen oxides, when released into the atmosphere, react with water vapor to form nitric acid. While the sulfuric acid component was likely dominant due to the specific geology of the impact site, nitric acid would have added to the overall acidity of the precipitation. The global wildfires, by burning vast amounts of vegetation, would have also released various acidic compounds into the atmosphere, further contributing to the overall chemical burden. Once formed, these sulfuric and nitric acid aerosols and gases were rapidly dispersed globally by high-altitude winds, ensuring that the acid rain was not a localized phenomenon but a worldwide environmental assault. When precipitation occurred, whether as rain, snow or fog, it would have been highly acidic, with pH levels potentially dropping to values as low as 0 or 1, comparable to battery acid. This level of acidity is far more extreme than typical acid rain caused by industrial pollution, which usually has a pH of around 4 or 5. The duration of this severe acid rain event is estimated to have lasted for several months to a few years, as the aerosols slowly settled out of the stratosphere. The impact of this highly acidic rain on terrestrial plants would have been devastating. Acid rain directly damages plant tissues, particularly leaves, by dissolving their protective waxy cuticles and interfering with their cellular processes. This would have led to widespread defoliation, stunted growth, and the death of many plant species. The acidification of soils would have also been a critical long-term effect. As acidic water percolated through the soil, it would have leached essential nutrients, making them unavailable for plant uptake. Furthermore, it would have mobilized toxic metals such as aluminum from the soil into solution, which could then be absorbed by plant roots, poisoning them. Plants that survived the initial impact and wildfires would have faced a severely compromised environment, struggling to grow in acidic, nutrient-depleted soils under conditions of prolonged darkness and extreme cold. Aquatic ecosystems, both freshwater and marine, were also profoundly affected by the acid rain. Freshwater lakes and rivers would have experienced rapid acidification, which is highly detrimental to aquatic life. Many fish, amphibians, and aquatic invertebrates are extremely sensitive to changes in pH. Acidification can disrupt their physiological functions, interfere with reproduction, and ultimately lead to widespread mortality. The sudden drop in pH would have caused a mass die-off of many freshwater species. In the oceans, the acid rain would have led to widespread ocean acidification, particularly in the surface layers. This is a critical concern because many marine organisms, from microscopic plankton to larger shellfish and corals, rely on calcium carbonate to build their shells and skeletons. As the ocean water becomes more acidic, the concentration of carbonate ions decreases, making it difficult for these organisms to form and maintain their calcium carbonate structures. In severe cases of acidification, existing shells and skeletons can even begin to dissolve. The collapse of calcifying plankton, such as coccolithophores, at the base of the marine food web would have had catastrophic cascading effects throughout the entire ocean ecosystem, leading to widespread starvation and extinction of larger marine life. Evidence for this ocean acidification is found in the fossil record, where the K-Peak boundary often shows a dramatic reduction or complete absence of calcifying marine microfossils. The pervasive and corrosive nature of the acid rain, acting in concert with the other environmental stresses, delivered a powerful blow to both terrestrial and aquatic life, contributing significantly to the global mass extinction event. The most fundamental and widespread consequence of the asteroid impact and its immediate environmental aftermath was a catastrophic food chain collapse that reverberated through nearly all ecosystems on Earth. This collapse was primarily driven by the prolonged absence of sunlight, which directly killed off plants, the irreplaceable base of nearly all food webs. Without primary producers to convert solar energy into organic matter, the entire intricate network of life that had flourished for millions of years rapidly unraveled, leading to the widespread starvation and extinction of larger animals. At the heart of this collapse lies the process of photosynthesis. Plants, including trees, ferns, grasses, and microscopic phytoplankton in the oceans, are autotrophs, meaning they produce their own food using sunlight, carbon dioxide, and water. They form the foundation of almost every ecosystem, converting inorganic matter into organic biomass that can be consumed by other organisms. Herbivores, or primary consumers, directly feed on plants, while carnivores, or secondary and tertiary consumers, feed on herbivores or other carnivores. This interconnected flow of energy from the sun, through plants, and up the food chain is what sustains virtually all complex life. The asteroid impact, the subsequent global wildfires, and the vaporization of sulfur-rich rocks injected immense quantities of dust, soot, and sulfuric acid aerosols into the atmosphere. This dense atmospheric veil created a global sunshade that effectively blocked out sunlight for an extended period. Climate models and geological evidence suggest that light levels at Earth's surface plummeted to near total darkness for several months, with significantly reduced light persisting for several years. This prolonged darkness rendered photosynthesis impossible or severely inhibited across the planet. The immediate and most devastating effect was the rapid death of plants. On land, trees, shrubs, and smaller vegetation, deprived of sunlight, would have quickly withered and died. Plants that survived the initial firestorms would have succumbed to starvation. The cold temperatures of the impact winter further exacerbated this plant die-off, as many Mesozoic plants were adapted to a consistently warm climate and were not tolerant of freezing conditions. The combination of darkness and cold created an environment where terrestrial plant life could not survive on a widespread scale. In the oceans, the collapse was equally severe. Microscopic phytoplankton, the primary producers of marine ecosystems, are highly dependent on sunlight penetrating the surface waters. When the sun was blocked, these tiny organisms, which form the base of the vast oceanic food web, perished en masse. Evidence for this marine collapse is starkly visible in the fossil record, where the KPG boundary marks a dramatic and sudden disappearance of many planktonic species. With the widespread death of plants, the entire food chain began to unravel from the bottom up. Herbivorous animals, which relied directly on plants for sustenance, would have quickly run out of food. Large herbivorous dinosaurs, such as the hadrosaurs and ceratopsians, required vast quantities of vegetation daily to sustain their enormous bodies. Without their primary food source, these giants would have faced rapid starvation. Their large size, which had been an evolutionary advantage for millions of years, became a fatal liability in a world devoid of food. The starvation of herbivores, in turn, led to the starvation of carnivorous animals. Large predatory dinosaurs like Tyrannosaurus rex and Giganotosaurus depended on the availability of large herbivorous prey. As their food sources dwindled and disappeared, these formidable predators would have also faced a rapid decline in available sustenance. Even scavengers would have eventually run out of carcasses as the initial wave of death subsided and no new food sources emerged. The interconnectedness of the food chain meant that the collapse at the base inevitably led to the collapse at higher trophic levels. The vulnerability to this food chain collapse was largely dependent on an organism's size and metabolic rate. Large animals, with their high energy demands and inability to find sufficient shelter or enter prolonged states of torpor, were particularly susceptible. Their massive bodies required continuous and substantial food intake, which became impossible in the post-impact world. In contrast, smaller animals, including early mammals, birds, and some reptiles and amphibians, had several advantages. Their lower metabolic rates meant they required less food to survive. Many could burrow underground, find shelter in caves, or enter states of hibernation or torpor, allowing them to ride out the worst of the darkness and cold. Furthermore, many small survivors were omnivores or detritivores, capable of subsisting on alternative food sources like seeds, insects, decaying organic matter, or even scavenging small carcasses, which provided a temporary buffer against the widespread plant die-off. The global food chain collapse, initiated by the sun-blocking atmospheric veil, was thus a primary and devastating mechanism of the KPG mass extinction, selectively wiping out the largest and most specialized animals while favoring the survival of smaller, more adaptable generalists. While the asteroid impact theory stands as the leading scientific explanation for the dinosaur extinction, another significant geological event that occurred around the same time has also been proposed as a primary or contributing cause: massive and prolonged volcanic eruptions. This alternative or complementary hypothesis centers on the colossal outpouring of lava and gases from a region known as the Deccan Traps, in what is now west-central India. The Deccan Traps represent one of the largest volcanic provinces on Earth, a vast area covered by successive layers of basaltic lava flows. These eruptions were not single, explosive events, but rather a series of effusive eruptions that occurred over an extended period, spanning roughly 1 million years across the Cretaceous-Paleogene boundary. The sheer volume of lava extruded was immense, estimated to be over 500,000 cubic kilometers, enough to cover an area the size of France to a depth of more than 1 kilometer. This scale of volcanism is known as a flood basalt event, and such events are associated with some of Earth's most significant environmental changes and mass extinctions throughout geological history. The primary way in which these massive volcanic eruptions could have influenced global climate and ecosystems was through the release of enormous quantities of gases and aerosols into the atmosphere. Unlike explosive volcanic eruptions that primarily inject ash and dust, effusive flood basalt eruptions release vast amounts of sulfur dioxide, carbon dioxide, and other volatile compounds. The release of sulfur dioxide would have had an immediate and significant cooling effect. Once in the stratosphere, sulfur dioxide reacts to form sulfuric acid aerosols, similar to those produced by the asteroid impact. These aerosols reflect incoming sunlight back into space, leading to a reduction in global temperatures. Depending on the intensity and duration of these sulfur emissions, this volcanic cooling could have caused episodes of volcanic winter, similar in effect to the impact winter, but potentially more prolonged and episodic. Evidence for such cooling events during the late Cretaceous has been found in some paleoclimate records. Conversely, the prolonged release of massive amounts of carbon dioxide, a potent greenhouse gas, would have had a long-term warming effect. While sulfur aerosols cause short-term cooling, carbon dioxide accumulates in the atmosphere and traps heat, leading to a gradual increase in global temperatures. This dual effect of volcanism, initial cooling from sulfur and long-term warming from carbon dioxide, could have subjected Earth's ecosystems to repeated and dramatic climate fluctuations. These shifts, from cold to warm and back again, would have placed immense stress on life forms, forcing them to constantly adapt to changing conditions. Such environmental instability could have weakened ecosystems, making them more vulnerable to subsequent shocks. The timing of the Deccan Traps eruptions relative to the KPG boundary has been a subject of intense scientific scrutiny. Precise radiometric dating of the lava flows indicates that the most intense phase of volcanism, where the vast majority of the lava was erupted, occurred in the last few 100,000 years of the Cretaceous, with a significant pulse occurring very close to, or even precisely at, the KPG boundary itself. This temporal overlap has led some scientists to argue that the Deccan Traps volcanism played a direct role in the mass extinction, either as the sole cause or as a significant contributing factor that pre-stressed ecosystems, making them more susceptible to the asteroid impact. Proponents of the volcano theory suggest that the cumulative effects of prolonged volcanic activity, repeated episodes of cooling and warming, ocean acidification from sulfur and carbon dioxide, and potentially acid rain, could have gradually weakened dinosaur populations and other life forms over hundreds of thousands of years. This long-term environmental degradation might have made them less resilient to any additional stressor, such as the asteroid impact. In this view, the asteroid impact might have been the final straw that pushed already struggling ecosystems over the brink. However, the volcano theory alone faces challenges in explaining certain aspects of the KPG extinction. While volcanism can cause climate shifts and extinctions, it typically results in a more gradual decline in biodiversity over hundreds of thousands or millions of years, rather than the sudden, synchronous, and global extinction event observed at the KPG boundary. Furthermore, the volcanic theory struggles to account for the specific geological markers found universally at the KPG boundary, such as the iridium anomaly, shocked quartz, and microtectites, which are definitive signatures of a hypervelocity impact and not volcanic activity. While large volcanic eruptions can release some iridium, it is not distributed globally in the same distinct layer, nor do they produce shocked quartz or microtectites. Current scientific consensus largely favours the asteroid impact as the primary and immediate cause of the KPG mass extinction, given the overwhelming and specific evidence for a sudden global impact event. However, many scientists acknowledge that the Deccan Traps volcanism was a major geological event occurring concurrently and may have played a significant role as a contributing factor. It is plausible that the prolonged environmental stresses from the Deccan eruptions, such as long-term climate fluctuations and ocean acidification, had already weakened ecosystems and dinosaur populations, making them more vulnerable to the sudden and catastrophic blow delivered by the asteroid impact. Thus, while the asteroid was the ultimate killing blow, the Earth's environment may have already been primed for disaster by the immense volcanic activity. The Earth's crust bears the scars of immense geological events, and among the most profound of these are large igneous provinces, vast regions where enormous amounts of molten rock have erupted onto the surface. One such province, of particular relevance to the dinosaur extinction, is the Deccan Traps, located in present-day west-central India. This specific volcanic region is characterized by monumental outpourings of lava that occurred around the very end of the Cretaceous period and the beginning of the Paleogene, making it a key player in scientific discussions about the KPG extinction event. The Deccan Traps are a prime example of a flood basalt province. Unlike the explosive conical volcanoes that are familiar today, flood basalt eruptions are characterized by vast diffusive flows of highly fluid, low-viscosity lava that erupt from fissures in the Earth's crust rather than from a central vent. These eruptions can continue for extended periods, releasing enormous volumes of molten rock that spread across vast areas, forming thick layered plateaus. The name Deccan Traps itself is derived from the Swedish word trap, meaning steps or stairs, referring to the step-like hills and valleys that characterize the landscape due to the erosion of successive horizontal lava flows. The scale of the Deccan Traps volcanism is truly immense. Today, the preserved portion of the flood basalts covers an area of approximately 500,000 square kilometers, roughly the size of France. However, geological evidence suggests that the original extent of the lava flows was far greater, potentially covering as much as 1.5 million square kilometers across what was then the Indian subcontinent. The total volume of lava erupted is estimated to be over 500,000 cubic kilometers, and some estimates push this figure as high as 1.5 million cubic kilometers. To put this into perspective, if 1.5 million cubic kilometers of lava were to cover an area the size of India, it would be approximately half a kilometer deep. This represents an almost unimaginable amount of molten rock pouring onto the Earth's surface over geological timescales. The timing of the Deccan Traps eruptions is crucial to their hypothesized role in the KPG extinction. Precise radiometric dating of the basaltic layers has shown that the volcanism occurred over a prolonged period, spanning roughly 1 million years across the Cretaceous-Paleogene boundary. However, the most intense phase of eruption, when the vast majority of the lava was extruded, appears to have occurred in the last few 100,000 years of the Cretaceous, with a significant pulse of activity occurring very close to, or even precisely at, the KPG boundary itself, approximately 66 million years ago. Some studies indicate that the eruptions intensified just before the asteroid impact, while others suggest a major pulse of volcanism may have been triggered or greatly enhanced by the seismic shock of the Chicxulub impact itself. This temporal overlap with the extinction event has placed the Deccan Traps at the forefront of the debate about the ultimate causes of the end Cretaceous mass extinction. The formation of the Deccan Traps is widely attributed to a mantle plume, a rising column of superheated rock originating from deep within Earth's mantle. As the Indian tectonic plate drifted northward during the Cretaceous, it passed over this stationary mantle plume, causing large-scale melting and the outpouring of magma. This plume is thought to be the same one that today fuels the active volcanoes beneath Reunion Island in the Indian Ocean. The continuous movement of the Indian plate over this hotspot created a trail of volcanic activity, with the Deccan Traps representing the largest and most significant manifestation of this geological process. The geological structure of the Deccan Traps is characterized by hundreds of individual lava flows, stacked one upon another like pancakes, often separated by thin layers of sedimentary rocks that represent periods of quiescence between eruptions. These layers can be tens of meters thick each, and the total thickness of the basalt pile can reach over 2,000 meters in some areas. Interspersed within the main lava flows are also evidence of dikes, which are vertical magma-filled cracks that fed the surface eruptions, and sills, which are horizontal magma intrusions into existing rock layers. The sheer volume and repetitive nature of these eruptions point to a deep and sustained magmatic source. While the immediate impact of lava flows would have caused localized devastation, incinerating everything in their path and creating vast barren landscapes, the global effects of the Deccan Traps volcanism were far more insidious and widespread. These global effects stemmed primarily from the enormous quantities of gases and aerosols released into the atmosphere during these prolonged eruptions. It is this atmospheric alteration, rather than the lava itself, that is considered the main way the Deccan Traps could have contributed to a global climate shift, and, consequently, to the mass extinction event. The close proximity in time of this massive volcanic activity to the KPG boundary ensures its prominent role in scientific discussions regarding the complex environmental pressures that contributed to the end of the dinosaur age. Massive volcanic eruptions, such as those that formed the Deccan Traps, are not only characterized by vast outpourings of lava, but also by the release of colossal quantities of gases into the atmosphere. These volcanic gases, often invisible but potent, have the capacity to significantly alter global climate patterns over various timescales, posing a serious threat to ecosystems. Understanding the types of gases emitted during flood basalt events and their atmospheric effects is central to appreciating their potential role in past climate shifts, including those around the time of the dinosaur extinction. The primary gases released during large-scale basaltic eruptions like the Deccan Traps include sulfur dioxide, carbon dioxide, halogens such as chlorine and fluorine, water vapor, and hydrogen sulfide. Each of these gases, once injected into the atmosphere, can initiate a chain of complex chemical reactions that collectively impact Earth's radiative balance and climate system. The sheer volume and prolonged nature of the Deccan eruptions meant that these gases were emitted continuously over hundreds of thousands of years, leading to cumulative and sustained environmental changes. Sulfur dioxide, or SO2, is one of the most climatically significant gases released during volcanic eruptions. When SO2 is injected into the upper atmosphere, particularly the stratosphere, it undergoes a series of chemical reactions, oxidizing to form tiny, highly reflective sulfuric acid aerosols. These microscopic droplets are extremely efficient at scattering incoming solar radiation back into space, preventing it from reaching Earth's surface. This process leads to a significant and rapid global cooling effect, often referred to as a volcanic winter. Historical volcanic eruptions, such as that of Mount Pinatubo in the Philippines in 1991, have demonstrated this cooling effect on a smaller scale, causing a measurable drop in global temperatures for a year or two. The Deccan Traps, however, release sulfur dioxide on an incomparably grander scale over prolonged periods, capable of inducing repeated and severe cooling episodes that could last for decades or even centuries. Beyond cooling, sulfur emissions also contribute directly to acid rain, When sulfuric acid aerosols combine with atmospheric water vapor, they form highly acidic precipitation. This acid rain, similar to that discussed in the context of the asteroid impact, would have damaged terrestrial plants by dissolving their waxy cuticles and interfering with their physiological processes. It would also have caused widespread acidification of freshwater lakes and rivers, harming aquatic life. In the oceans, massive influxes of sulfur could lead to ocean acidification, stressing calcifying marine organisms like plankton and corals that rely on calcium carbonate for their shells and skeletons. Carbon dioxide, or CO2, is another major volcanic gas with profound climatic implications. Unlike sulfur aerosols, which cause relatively short-term cooling, carbon dioxide is a potent greenhouse gas that traps heat in the atmosphere. It has a much longer atmospheric residence time, meaning it remains in the atmosphere for hundreds of thousands to millions of years before being naturally removed. The sustained, enormous emissions of carbon dioxide from the Deccan Traps volcanism would have led to a gradual long-term increase in global average temperatures, contributing to a hothouse effect. While volcanic cooling might occur immediately after a major eruptive pulse, the cumulative effect of constant CO2 release over 1 million years would be a significant warming trend. Such warming can lead to ocean deoxygenation, where warmer waters hold less dissolved oxygen, creating anoxic, oxygen-depleted zones that are detrimental to marine life. It also contributes to further ocean acidification, stressing calcifying organisms. Other volcanic gases, while perhaps less dominant in their climate impact compared to sulfur dioxide and carbon dioxide, can also play a role. Halogens like chlorine and fluorine can form hydrochloric and hydrofluoric acids, which contribute to acid rain and can also have direct toxic effects on organisms. Some of these gases, especially chlorine, can also contribute to ozone layer depletion, potentially increasing harmful ultraviolet radiation reaching Earth's surface. Hydrogen sulfide is a toxic gas that can directly poison organisms if present in high concentrations. The sheer magnitude of gas release from the Deccan Traps is what makes them so significant in climate discussions. It was not a single, isolated event, but a continuous series of enormous pulses of gas emissions over hundreds of thousands of years. This sustained input of climate-altering gases into the atmosphere would have created an environment of chronic stress, characterized by repeated shifts between cooling and warming. Evidence for these ancient gas emissions comes from geochemical analyses of the Deccan basalts themselves, which contain preserved gas bubbles, and from proxy records found in ancient sediments that reflect atmospheric composition and climate conditions during the late Cretaceous. The powerful, persistent atmospheric alterations caused by these volcanic gases illustrate how large-scale geological processes can profoundly influence Earth's climate and ultimately impact the course of life. The sustained and massive volcanic eruptions of the Deccan Traps, occurring around the end of the Cretaceous period, possessed the capacity to induce significant and complex climate shifts on a global scale. These shifts would not have been a simple, unidirectional change, but rather an oscillating pattern of cooling and warming, depending on the relative balance and timing of different gas emissions. This chronic environmental instability, lasting for hundreds of thousands of years, could have placed immense stress on Earth's ecosystems, potentially preconditioning them for a major extinction event. The dual nature of volcanic climate forcing is critical to understanding these shifts. As discussed, large-scale basaltic volcanism releases both sulfur dioxide and carbon dioxide, which have opposing effects on global temperatures. The immediate and generally short to medium-term effect is typically cooling, driven by sulfur dioxide. When vast quantities of sulfur dioxide are injected into the stratosphere, they oxidize to form sulfuric acid aerosols. These aerosols act like tiny mirrors, reflecting incoming solar radiation back into space. This reduction in solar energy reaching Earth's surface causes global temperatures to plummet, leading to volcanic winter conditions. These periods of cold could last from a few months to several years, depending on the intensity and duration of the eruptive pulse. Evidence from geological records such as changes in marine plankton communities and isotopic signatures in sediments suggests that there were multiple cooling events during the last 1 million years of the Cretaceous, broadly correlating with phases of intensified Deccan volcanism. These cooling periods would have disrupted plant growth, caused die-offs in temperature-sensitive species, and put stress on food chains. Conversely, the long-term effect of sustained volcanism is global warming, driven by the continuous release of colossal amounts of carbon dioxide. Carbon dioxide is a potent greenhouse gas that traps heat in the atmosphere. Unlike sulfur aerosols, which eventually settle out, carbon dioxide persists in the atmosphere for hundreds of thousands to millions of years. Over the prolonged eruptive history of the Deccan Traps, the cumulative release of CO2 would have led to a gradual increase in global average temperatures. This hothouse effect could have pushed Earth's climate towards warmer states, potentially creating conditions of extreme heat stress for some organisms. Evidence for a general warming trend leading into the KPG boundary has been found in some paleoclimate records, which could be attributed to Deccan CO2 emissions. Therefore, the Deccan Traps volcanism likely did not cause a single, monotonic climate change, but rather a series of rapid, short-term cooling events, punctuated by longer-term gradual warming trends. This created a climate characterized by significant oscillations and instability. Ecosystems would have been subjected to repeated shifts between relatively warmer periods, possibly leading to ocean anoxia, oxygen depletion, and acidification due to higher CO2, and colder periods marked by volcanic winters. This constant fluctuation between environmental extremes would have presented significant challenges for life. Organisms adapted to stable conditions, or those with narrow temperature tolerances, would have struggled to cope with these rapid and recurring changes. These long-term climate shifts would have manifested in various ways across different ecosystems. On land, changes in temperature and precipitation patterns could have altered major biomes. Forests might have been replaced by more open woodlands or grasslands during cooler, drier phases, or expanded during warmer, wetter periods. This would have directly impacted the distribution and availability of food for herbivorous dinosaurs, potentially leading to regional extinctions or forcing migrations. The physiological stress on dinosaurs, particularly the larger ones, from adapting to fluctuating temperatures, could have impacted their health, growth rates, and reproductive success. In marine environments, the climate shifts caused by volcanism would have led to significant disruptions. Periods of global warming, driven by volcanic CO2, would have contributed to ocean acidification, harming calcifying organisms like plankton and corals. Warmer ocean waters also hold less dissolved oxygen, potentially creating widespread noxic zones in the deep ocean, which are deadly to most marine life. Conversely, periods of volcanic cooling would have affected temperature-sensitive marine species, particularly those in shallow warm water environments. The repeated changes in ocean chemistry and temperature would have destabilized marine food webs, leading to significant declines in biodiversity long before the asteroid impact. The debate about the role of these volcanic climate shifts in the KP extinction often revolves around their timing relative to the Chicxulub impact. While the asteroid impact provides a compelling explanation for the suddenness and global synchronicity of the extinction, many scientists acknowledge that the sustained volcanic activity of the Deccan Traps could have acted as a pre-stressing factor. The argument is that ecosystems and dinosaur populations, already weakened by hundreds of thousands of years of chronic climate instability, ocean acidification, and other environmental pressures from the Deccan volcanism, were rendered more vulnerable to the final, catastrophic blow delivered by the asteroid. Thus, the Deccan Traps climate shifts are viewed not necessarily as the sole cause, but as a significant underlying factor that primed the planet for one of the most profound biological crises in its history. While the asteroid impact theory, supported by overwhelming geological evidence, is the leading scientific explanation for the end Cretaceous mass extinction, over the years, various other theories have been proposed to explain the disappearance of the dinosaurs. Some of these ideas were once popular but have since been largely superseded by the impact hypothesis, while others are considered complementary factors that might have contributed to the overall environmental stress leading up to the catastrophe. Providing a comprehensive overview necessitates briefly addressing these alternative or contributing hypotheses to understand the full scope of scientific inquiry into this profound event. One prominent alternative theory that gained traction before the asteroid impact hypothesis was the idea of widespread disease outbreaks. This theory posited that a highly virulent pathogen, perhaps a virus or bacterium, could have swept through dinosaur populations, causing a pandemic that led to their demise. The concept is appealing because diseases can be highly effective at wiping out populations, especially if the animals lack immunity. However, this theory faces significant challenges. For a disease to cause a mass extinction of the scale seen at the KPG boundary, it would need to be incredibly potent and capable of affecting a vast array of species across different continents and environments, including terrestrial and marine life. Pathogens are typically host-specific, meaning a single disease is unlikely to simultaneously decimate diverse groups like dinosaurs, pterosaurs, marine reptiles, and various marine invertebrates. Furthermore, proving a prehistoric pandemic through the fossil record is exceptionally difficult, as diseases rarely leave direct fossil evidence. While localized disease might have affected specific populations, it is highly improbable that a single disease could have caused a global, simultaneous extinction of such diverse groups. Another frequently discussed theory involves significant changes in sea levels, specifically a phenomenon known as marine regression. This theory suggests that a prolonged and widespread drop in global sea levels during the late Cretaceous could have contributed to the extinction. As sea levels fell, vast areas of shallow continental shelf environments, which were rich in biodiversity and served as important habitats and breeding grounds for many marine and coastal species, would have been exposed and dried out. This loss of habitat would have placed immense stress on marine life, potentially leading to widespread extinctions in the oceans. On land, a significant sea level drop could have altered coastal climates, reduced humidity, and created new land bridges, facilitating the spread of diseases or invasive species. While geological evidence does indicate some degree of marine regression during the late Cretaceous, it was a relatively gradual process, occurring over millions of years, not a sudden event. This gradual nature makes it difficult for marine regression alone to explain the abruptness and global synchronicity of the KPG extinction, which saw the simultaneous disappearance of both marine and terrestrial groups. Furthermore, the fossil record does not show a clear correlation between the timing of sea level changes and the sudden, widespread disappearance of all non-avian dinosaurs. Related to sea level changes is the broader concept of gradual climate change. Before the asteroid impact theory gained prominence, many scientists believed that long-term shifts in Earth's climate during the late Cretaceous could have slowly weakened dinosaur populations. This could have involved either a gradual cooling trend or increasing climatic variability, leading to harsher seasons. Such changes might have altered vegetation patterns, reduced food availability, or created physiological stress for animals adapted to a consistently warm, stable climate. For example, some researchers hypothesized that a cooling trend might have particularly affected large dinosaurs, which would have struggled to regulate their body temperatures in colder conditions. While paleoclimate data do show some fluctuations in temperature during the late Cretaceous, these changes were generally gradual and occurred over millions of years, allowing ample time for adaptation and evolution. They do not account for the sudden, sharp, and global nature of the KPG extinction event, where diverse groups vanished simultaneously. The fossil record of dinosaurs leading up to the KPG boundary does not consistently show a long, drawn-out decline in diversity or abundance that would be expected from gradual climate change alone. The role of massive volcanic activity, particularly the Deccan Traps eruptions in India, is another theory that has evolved from an alternative explanation to a potentially complementary one. Initially, some scientists proposed that the Deccan Traps volcanism was the sole cause of the extinction, arguing that the immense release of gases like sulfur dioxide and carbon dioxide could have caused severe climate shifts, acid rain, and ocean acidification. While the scale of the Deccan eruptions was indeed monumental and capable of altering global climate, the timing and nature of the extinction event present challenges for volcanism as the sole cause. Volcanic extinctions tend to be more drawn out, occurring over hundreds of thousands or millions of years, and they do not produce the unique global impact signatures like iridium anomalies and shocked quartz. However, many scientists now agree that the Deccan volcanism likely played a significant contributing role. The prolonged environmental stresses from these eruptions, such as long-term climate fluctuations and ocean acidification, could have weakened ecosystems and dinosaur populations, making them more vulnerable to the final catastrophic blow delivered by the asteroid impact. In this view, the asteroid was the immediate trigger, but the Earth's environment might have already been primed for disaster by the immense volcanic activity. Another set of ideas focused on biological interactions, such as competition with mammals or egg predation. It was once suggested that the rise of mammals, which were diversifying during the Cretaceous, might have outcompeted dinosaurs for resources or preyed heavily on dinosaur eggs, preventing their reproduction. However, this theory is largely unsupported by the fossil record. Cretaceous mammals were generally small, nocturnal, and occupied very different ecological niches from the large, dominant dinosaurs. There is no evidence that they posed a significant competitive threat to the vast array of dinosaur species. Similarly, while some mammals and other small animals undoubtedly preyed on dinosaur eggs, there is no indication that this predation was widespread enough or severe enough to cause the extinction of entire dinosaur lineages across the globe simultaneously. Such factors might have contributed to localized pressures, but they cannot explain a mass extinction event of this magnitude. Finally, some theories have proposed multiple asteroid impacts or a comet shower, rather than a single large asteroid. While the solar system has certainly experienced periods of increased impact rates throughout its history, the overwhelming evidence at the KP boundary points to a single, exceptionally large impact event as the primary trigger. The Chicxulub crater is the only known impact structure of the appropriate size and age to explain the global signatures of the KP boundary. While smaller impacts might have occurred, they would not have had the same global catastrophic effect. Thus, while various ideas have been explored, the asteroid impact, potentially exacerbated by ongoing Deccan volcanism, remains the most robust and scientifically supported explanation for the abrupt end of the dinosaur age. The end Cretaceous mass extinction event, approximately 66 million years ago, was a highly selective catastrophe. While it wiped out all non-avian dinosaurs and many other groups, some forms of life survived and even thrived in the aftermath. Analysing why large dinosaurs in particular were especially vulnerable to the sudden and drastic environmental changes caused by the asteroid impact is crucial for understanding the selective nature of this extinction. Their size, specialised diets, reproductive strategies, and inability to find adequate shelter all contributed to their demise. One of the most critical factors contributing to the vulnerability of large dinosaurs was their immense size and corresponding high metabolic demands. Dinosaurs like Tyrannosaurus rex and Triceratops, weighing many tons, required vast quantities of food daily to sustain their enormous bodies. When the asteroid impact plunged the Earth into prolonged darkness and extreme cold, photosynthesis, the base of the food chain, effectively ceased. Plants died off en masse, leading to a rapid and widespread collapse of food sources. Large herbivores, dependent on an abundant supply of vegetation, would have quickly starved. Their sheer bulk meant they could not survive for long periods without food, unlike smaller animals with lower energy requirements. The subsequent starvation of herbivores then led to the starvation of large carnivores, who relied on these herbivores for sustenance. The larger an animal, the more food it needs, and the more vulnerable it becomes when that food supply vanishes globally. The specialised diets of many large dinosaurs also played a significant role in their vulnerability. Many herbivorous dinosaurs were adapted to specific types of vegetation, such as conifers or particular flowering plants. When these specific food sources disappeared due to the darkness and cold, these specialised herbivores had no alternative. Similarly, large carnivores were often specialised predators of large herbivores. When their primary prey starved, they too faced an impossible situation. In contrast, many of the surviving animals were generalists or omnivores, capable of eating a wider variety of foods, including seeds, insects, decaying organic matter, or small carcasses, which provided a temporary buffer against the widespread plant die-off. Their less specialised diets allowed them greater flexibility in a world where familiar food sources had vanished. Another critical factor was the inability of large dinosaurs to find adequate shelter from the immediate and prolonged environmental assaults. The initial impact generated a global thermal pulse, a rain of fire from re-entering ejecta, which would have incinerated any exposed life. Large dinosaurs, unable to burrow underground or seek refuge in small crevices, would have been directly exposed to this intense heat. Even if they survived the initial heat, they faced the subsequent impact winter, a period of extreme cold and darkness. Large animals lose heat more slowly than small ones, but they also have a smaller surface area to volume ratio, making it harder to dissipate heat when it's too hot, and harder to generate enough internal heat to stay warm when it's too cold, especially if they are not fully endothermic or if their food supply is cut off. Small animals like early mammals, lizards, snakes, and amphibians had the distinct advantage of being able to burrow deep into the ground, hide in caves, or seek refuge in water bodies, insulating them from the worst of the heat and cold. Many could also enter states of torpor or hibernation, significantly reducing their metabolic rate and energy requirements during the period of food scarcity. The reproductive strategies of large dinosaurs also contributed to their vulnerability. Dinosaurs laid large eggs, and their offspring often took many years to reach maturity. This meant that their populations had relatively long generation times and slower reproductive rates compared to smaller animals. In a catastrophic event that wiped out most adults, the slow reproductive cycle of large dinosaurs would have made it extremely difficult for their populations to recover. Even if some eggs or juveniles survived, the lack of food and suitable habitat for growing young would have prevented successful recruitment into the next generation. In contrast, many surviving groups, such as small mammals and birds, have much shorter gestation periods, lay smaller eggs, or give live birth to small young, and mature much faster. This allowed them to reproduce more quickly and re-establish populations in the changed environment. Furthermore, the global nature of the extinction event meant there were no safe refuges for large dinosaurs. The atmospheric veil of dust, soot, and aerosols affected the entire planet, leading to worldwide darkness, cold, and acid rain. There was no continent or region where large dinosaurs could escape the environmental collapse. This lack of geographical refuge meant that even if a few individuals survived in one area, the widespread destruction of their food sources and habitat across the globe prevented any meaningful long-term survival or recovery of their species. Finally, while the precise physiology of dinosaurs is still debated, their large size may have made them more susceptible to rapid environmental shifts, regardless of whether they were warm-blooded or cold-blooded. Large ectotherms, cold-blooded animals, would struggle to maintain body temperature in extreme cold. Large endotherms, warm-blooded animals, would face immense challenges in finding enough food to fuel their high metabolic rates in a world devoid of vegetation. In essence, the very adaptations that allowed dinosaurs to dominate for over 165 million years, their size, specialization, and reliance on abundant plant life, became their greatest weaknesses in the face of a sudden global environmental catastrophe. The extinction was a selective filter, favoring the small, the generalist, the burrower, and the aquatic, while eliminating the giants of the Mesozoic. The end Cretaceous mass extinction event, approximately 66 million years ago, was a highly selective but devastating biological crisis that marked the complete and utter disappearance of all non-avian dinosaurs from the face of the Earth. This means that every single species of dinosaur, except for the lineage that evolved into modern birds, vanished from the fossil record at or just above the Cretaceous-Paleogene boundary. The extinction was comprehensive for this group, leaving no non-avian dinosaur survivors to continue their reign into the Cenozoic era. Among the most iconic groups that completely vanished were the large dominant theropods, the beast-footed carnivorous dinosaurs. This includes the famous Tyrannosaurus rex, the apex predator of late Cretaceous North America, known for its massive jaws and bone-crushing bite. Other large theropods like Giganotosaurus from South America and Spinosaurus from North Africa, both formidable predators in their respective ecosystems, also disappeared entirely. The agile sickle-clawed dromaeosaurids, often referred to as raptors, such as Velociraptor and Deinonychus, which were highly successful predators of smaller prey, also failed to survive the extinction event. All other theropod lineages, including the ostrich-like ornithomimids and the large feathered oviraptorosaurs, similarly vanished, leaving only their avian descendants. The diverse and abundant herbivorous dinosaurs were also entirely wiped out. This includes all species of hadrosaurs, the duck-billed dinosaurs, which were the dominant large plant eaters in many late Cretaceous ecosystems. Genera like Edmontosaurus and Parasaurolophus, known for their elaborate crests and sophisticated dental batteries, disappeared completely. Similarly, all ceratopsians, the horned dinosaurs, met their end. This group included the massive Triceratops, with its distinctive 3 horns and large frill, and other species like Styracosaurus and Pachyrhinosaurus. These powerful herbivores, despite their formidable defences, could not withstand the global environmental collapse. The heavily armoured dinosaurs, the ankylosaurs, also vanished. These living tanks, such as Ankylosaurus itself, with their extensive bony plates and powerful tail clubs, were well protected against predators, but proved vulnerable to the widespread starvation caused by the collapse of plant life. Pachycephalosaurs, the dome-headed dinosaurs, known for their thick skulls, also disappeared from the fossil record. Even the remaining sauropods, the long-necked giants that had dominated the Jurassic, were completely wiped out. While their greatest diversity was in the Jurassic, some sauropod lineages, such as the Titanosaurs, persisted into the late Cretaceous, but none survived the KPG event. Beyond the non-avian dinosaurs, the extinction event also claimed many other prominent groups of Mesozoic reptiles. All pterosaurs, the flying reptiles that had soared through the skies for over 100 million years, were completely wiped out. This includes giants like Quetzalcoatlus, with its enormous wingspan, and smaller forms like Pteranodon. Their disappearance left the skies open for the diversification of birds, which are the only surviving dinosaur lineage. In the oceans, the extinction was equally devastating for large marine reptiles. All mosasaurs, the formidable serpentine marine predators that had become the apex predators of the late Cretaceous seas, vanished entirely. Similarly, all plesiosaurs, the long-necked and short-necked marine reptiles that had been a diverse group throughout the Mesozoic, also disappeared. Their extinction opened up ecological niches that would later be filled by marine mammals like whales and seals. The marine realm also saw the complete extinction of ammonites, a group of shelled cephalopods related to modern squids and octopuses. Ammonites had been incredibly diverse and abundant throughout the Mesozoic, serving as important index fossils for geological dating. Their sudden and complete disappearance at the KPG boundary is a stark indicator of the severity of the marine extinction. Many groups of marine plankton, particularly calcifying forms like Foraminifera and coccolithophores, also suffered catastrophic losses, with some groups experiencing near-total extinction. This collapse at the base of the marine food web had cascading effects on all higher marine life. While the extinction was devastating for these groups, it is equally important to note what did survive. The lineage of dinosaurs that evolved into modern birds was the sole exception among the Dinosauria. Small feathered theropods, the ancestors of birds, managed to survive the catastrophe, likely due to their smaller size, ability to fly, and more generalized diets. Other survivors included small mammals, which were generally burrowing and omnivorous, allowing them to escape the immediate heat and find alternative food sources. Crocodilians, turtles, snakes, lizards, and amphibians also largely survived, often due to their semi-aquatic lifestyles, ability to burrow, or lower metabolic rates. Most fish, sharks, and many invertebrates also persisted, though with significant losses in some groups. The selective nature of the KPG extinction thus entirely removed the dominant large reptiles of the Mesozoic, paving the way for the Cenozoic era and the subsequent diversification of mammals and birds. The end Cretaceous mass extinction event, approximately 66 million years ago, was a period of immense global devastation, yet it was not an absolute annihilation of all life. While many prominent groups, most notably all non-avian dinosaurs, vanished completely, a significant portion of Earth's biodiversity managed to survive the catastrophe. Analysing the characteristics of these survivors provides crucial insights into the selective nature of the extinction event and the traits that conferred resilience in the face of unprecedented environmental upheaval. The animals that successfully navigated this global crisis were generally small, adaptable, and often possessed the ability to find shelter or subsist on varied food sources. Among the most significant survivors were the ancestors of modern birds. Birds are, in fact, the direct descendants of small feathered theropod dinosaurs. While their larger non-avian relatives perished, the lineage leading to birds managed to persist. This survival is attributed to several key factors: birds were generally small, allowing them to find refuge in burrows, under debris, or in aquatic environments, protecting them from the immediate heat and blast. Their ability to fly would have allowed them to escape localized dangers and potentially seek out scattered food resources. Furthermore, many early birds were likely generalists in their diet, consuming seeds, insects, or small invertebrates, which would have been more readily available in the post-impact world than the large quantities of vegetation required by big herbivores. Their high metabolic rates, coupled with their small size, meant they could survive on less food for a period, and their rapid reproductive cycles allowed for quicker population recovery. Small mammals also emerged as clear winners in the post-extinction world. Throughout the Mesozoic era, mammals had been relatively small, mostly nocturnal, and occupied niches largely overshadowed by dinosaurs. However, their small size proved to be a critical advantage during the extinction event. Like birds, small mammals could burrow underground, providing insulation from the intense heat of the initial firestorm and the subsequent freezing temperatures of the impact winter. Their nocturnal habits might have also protected them from the immediate blinding flash and heat of the impact. Many early mammals were omnivorous or insectivorous, meaning they could subsist on a varied diet of seeds, roots, insects, or decaying organic matter. Food sources that were more likely to persist or reappear quickly in the devastated landscape than large quantities of fresh vegetation. Their relatively high reproductive rates and short generation times also enabled them to rapidly diversify and fill the ecological vacuum left by the dinosaurs. Reptiles, other than non-avian dinosaurs, also saw significant survival rates, though with some losses. Crocodilians, including alligators and crocodiles, largely survived. Their semi-aquatic lifestyle provided protection from the initial heat and fires, and their ability to enter states of torpor or brumation, a reptilian form of hibernation, would have allowed them to endure periods of food scarcity and cold. Their diet, often consisting of fish and carrion, also offered more flexibility in a disrupted ecosystem. Turtles and tortoises, with their protective shells and ability to burrow or retreat into water, also fared relatively well. Snakes and lizards, generally small and capable of burrowing into soil or hiding in crevices, also survived the catastrophe. Their lower metabolic rates compared to dinosaurs meant they could survive on less food for longer periods. Amphibians such as frogs, salamanders, and caecilians also showed high survival rates. Their reliance on moist environments, often near freshwater bodies, and their ability to burrow into mud or soil protected them from the immediate atmospheric and thermal shocks. Their diet of insects and other small invertebrates, which might have been more resilient in the immediate aftermath, also contributed to their survival. Fish, both freshwater and marine, generally survived the extinction event, although marine fish populations experienced significant losses, particularly among species dependent on plankton, that collapsed at the base of the food web. Freshwater fish, often living in more buffered environments, fared better. Sharks and rays, which are cartilaginous fish, also showed high survival rates, possibly due to their broad diets and adaptability. The deep ocean, largely unaffected by the immediate surface devastation, also served as a refuge for many marine species. In terms of plant life, the extinction was devastating for many groups, but not absolute. While large forests of conifers, cycads, and ferns were largely incinerated or died from darkness and cold, some hardy plant lineages survived. Spore-producing plants such as ferns and mosses often have resilient spores that can lie dormant for long periods and rapidly colonize disturbed environments. The fern spike in the KPG boundary layer, a sudden increase in fern spores, indicates that ferns were among the first plants to recover and dominate the devastated landscapes. Seeds, particularly those from flowering plants, also played a crucial role in survival. Seeds can remain dormant for extended periods, waiting for favorable conditions to germinate, and they can be dispersed widely. While many flowering plant species went extinct, the group as a whole survived, and would later diversify rapidly in the Paleogene. The common threads among the survivors are clear: small size, which allowed for shelter and lower energy demands; generalized or diverse diets, providing flexibility in food sources; and the ability to find refuge from extreme environmental conditions, whether by burrowing, living in water, or entering dormant states. These characteristics proved to be critical adaptations that allowed certain lineages to weather the storm of global catastrophe, ensuring the continuity of life and setting the stage for the subsequent evolutionary radiation of mammals and birds in the Cenozoic era. The end Cretaceous mass extinction event, which eliminated all non-avian dinosaurs, marine reptiles, pterosaurs, and numerous other groups, created an unprecedented ecological opportunity that directly led to the rapid diversification and eventual dominance of mammals. For over 165 million years during the Mesozoic era, mammals had existed alongside dinosaurs, but they were largely relegated to small, nocturnal, and often insectivorous or omnivorous niches. The sudden removal of their reptilian overlords left a vast ecological vacuum, allowing mammals to expand into a multitude of new forms and lifestyles. During the Mesozoic, mammals were typically small, often no larger than a house cat, and many were shrew-like or rodent-like in appearance. They were generally overshadowed by the much larger and more diverse dinosaurs, which occupied the dominant roles in terrestrial ecosystems. Early mammals were characterized by traits that would later prove advantageous during the extinction. They were warm-blooded, allowing them to maintain a stable body temperature independently of their environment. They possessed fur for insulation, and many were nocturnal, which might have protected them from the immediate heat and blast of the asteroid impact. Their reproductive strategy, involving live birth and parental care, also offered certain advantages. The extinction of the dinosaurs at the KPG boundary removed the primary predators and competitors that had suppressed mammalian evolution for so long. Suddenly, the world was open. The ecological niches previously occupied by large herbivorous dinosaurs, such as browsing and grazing, and by large carnivorous dinosaurs such as apex predation, became vacant. This absence of dominant competitors allowed the surviving small mammals to undergo an explosive period of adaptive radiation, diversifying rapidly into a wide array of new forms and sizes. This period of rapid evolution and diversification began almost immediately in the Paleogene period, the first epoch of the Cenozoic era. One of the most significant changes was the increase in mammalian body size. With the largest land animals gone, there was no longer an ecological barrier preventing mammals from growing larger. Within a few million years after the extinction, mammals evolved to fill the roles of large herbivores and carnivores. Early Paleocene mammals were still relatively small, but by the Eocene epoch, which followed the Paleocene, massive mammals had emerged. For example, large browsing mammals, some resembling early rhinoceroses or elephants, began to appear. These included early ungulates, the ancestors of modern hoofed animals, which diversified to consume the recovering plant life. The diversification also extended to dietary specializations. Mammals evolved into dedicated herbivores, developing specialized teeth and digestive systems for processing various types of plant material, from leaves and fruits to grasses that would later become widespread. They also evolved into powerful carnivores, developing sharp teeth and claws for hunting prey. The rise of predatory mammals such as early creodonts and later carnivorans mirrored the ecological roles once held by theropod dinosaurs. These early mammalian predators became the new apex predators of the Cenozoic landmasses. The evolution of new locomotor styles was another key aspect of mammalian diversification. While Mesozoic mammals were primarily terrestrial, scurrying through the undergrowth, the Cenozoic saw the evolution of mammals adapted for a wide range of environments. Some mammals evolved to become arboreal, living in trees, leading to the development of primates. Others became adapted for aquatic life, leading to the evolution of whales and dolphins, filling the niches vacated by marine reptiles. Still others developed adaptations for flight, with bats becoming the only group of flying mammals. This broad expansion into different habitats and lifestyles was a direct consequence of the removal of the dominant reptilian groups. The Cenozoic era is often referred to as the Age of Mammals, precisely because of this rapid and widespread diversification. The absence of dinosaurs allowed mammals to become the dominant large terrestrial vertebrates, shaping ecosystems in ways they never could during the Mesozoic. This ecological release meant that the evolutionary pressures that had kept mammals small and in the shadows were removed, allowing their inherent biological advantages, such as warm-bloodedness, more efficient parental care, live birth and lactation, and larger brains, to come to the forefront. These traits, while present in Mesozoic mammals, became significant drivers of their evolutionary success in the post-extinction world. The rise of mammals was not just about size, it was about the evolution of complex social behaviours, intelligence, and a wide array of adaptations that allowed them to colonize virtually every terrestrial and aquatic environment. From the smallest shrews to the largest whales, and from burrowing moles to soaring bats, the diversity of modern mammals is a direct legacy of the ecological opportunity created by the extinction of the dinosaurs. Without that catastrophic event, the evolutionary trajectory of life on Earth would have been dramatically different, and the world we inhabit today, dominated by mammals, might never have come to be. The immediate aftermath of the end Cretaceous mass extinction, approximately 66 million years ago, left Earth a profoundly altered and devastated planet. The world that emerged from the global catastrophe was a stark contrast to the lush, dinosaur-dominated ecosystems of the late Cretaceous. This new Earth was characterized by widespread environmental destruction, a drastically reduced biodiversity, and a landscape slowly recovering from the combined assaults of impact, fire, darkness, cold, and acid rain. However, this period of devastation also represented a blank slate, an ecological vacuum that would eventually be filled by new forms of life, leading to the Cenozoic era, the age of mammals and birds. Immediately after the impact, the planet was plunged into a period of extreme darkness and cold, the impact winter. Sunlight was blocked by a dense atmospheric veil of dust, soot, and sulfur aerosols. This meant that for months, and possibly years, the Earth's surface received little to no direct solar radiation. Temperatures plummeted globally, reaching freezing levels even in tropical regions. This combination of darkness and cold led to the widespread death of terrestrial plants, which formed the base of most food chains. Forests were either incinerated by global wildfires or died from lack of light and freezing temperatures. The landscape would have been largely barren, covered in ash and the skeletal remains of dead vegetation. In the oceans, the situation was equally dire. The collapse of phytoplankton, the microscopic primary producers, due to lack of sunlight, led to the widespread starvation of marine life. Ocean acidification, caused by sulfuric acid rain, further stressed marine organisms, particularly those that built shells or skeletons from calcium carbonate. The surface waters of the oceans would have been cold and acidic, with vast areas of marine snow, dead organic matter, raining down from the dying surface layers to the deep sea. The immediate survivors of this planetary cataclysm were typically small, adaptable, and often capable of finding shelter. Small mammals, birds, crocodiles, turtles, snakes, lizards, amphibians, and many fish species persisted. These creatures often had lower metabolic rates, could burrow underground or retreat into water, and had more generalized diets that allowed them to subsist on alternative food sources like seeds, insects, or decaying organic matter. The large specialized dinosaurs, pterosaurs, and marine reptiles, unable to find refuge or sufficient food, had perished. The landscape of the new Earth would have been one of desolation and slow recovery. The fern spike in the fossil record, a sudden abundance of fern spores immediately above the KPG boundary, suggests that ferns were among the first plants to recolonize the devastated landscapes. Ferns are resilient pioneer species, capable of rapidly colonizing disturbed ground from dormant spores. As conditions slowly improved, with dust settling and temperatures gradually rising, other hardy plants, particularly those that could grow from seeds that survived the catastrophe, would have begun to re-establish themselves. This initial recovery would have been slow and patchy, with vast areas remaining barren for extended periods. The ecological niches left vacant by the extinction of the dinosaurs were immense. The absence of large herbivores meant that vegetation, once it began to recover, would have grown unchecked in many areas. The absence of large predators removed the top-down control on smaller animals. This created an unprecedented opportunity for the surviving lineages to diversify and fill these newly available roles. The most significant beneficiaries of this ecological vacuum were the mammals. From their small, nocturnal, and often insectivorous origins in the Mesozoic, mammals rapidly began to increase in size and diversify into a wide array of forms. Within a few million years, early Paleocene mammals started to grow larger, with some species reaching the size of bears or small cows. They evolved into new herbivorous forms, grazing on the recovering vegetation, and new carnivorous forms, preying on the growing populations of herbivores. This rapid adaptive radiation of mammals led to the emergence of diverse groups that would eventually give rise to all modern mammalian orders, including primates, ungulates, carnivores, and marine mammals. Birds, the surviving lineage of dinosaurs, also underwent a significant diversification in the Paleogene, filling many of the aerial niches vacated by the pterosaurs. Their ability to fly allowed them to quickly spread across the recovering landscapes and oceans. Other surviving groups like snakes and lizards also diversified, becoming more prominent in the terrestrial ecosystems. The new Earth was a world in transition, a testament to both the destructive power of a global catastrophe and the incredible resilience of life. The initial period of devastation gradually gave way to a phase of ecological restructuring, as surviving lineages adapted and diversified to fill the empty niches. This process of recovery and diversification ultimately led to the establishment of the modern ecosystems we see today, with mammals and birds as the dominant large terrestrial vertebrates, a direct legacy of the extinction event that ended the age of dinosaurs.